with AVS. You've probably seen an email from me about logging in for this best known practices for high vacuum workflows, and we are going to get started now. So I'm going to read some intro slides for you. This course is being taught by Gerardo Brucker. He's with MKS. We'd like to welcome you to this webinar, and if it's your first one, thank you for coming, and we hope to have you on some more. Just some information. To ask a question during the webinar, you may type it into the Q&A box on the right-hand side. Please reference the slide number when possible and send to all panelists. Gerardo is going to be taking some breaks throughout the webinar, and after those breaks, he'll be answering some questions. There will be about 3 10-minute breaks. This may be used for you to step out as needed, and again, he'll answer some questions at the end of these breaks and before he starts the next section. Gerardo, can you switch slides?
Yeah, I'm sorry.
Thank you. All right, we have some upcoming short course programs in 2020. This is our last short course type of training for the 2019 year. So we'll have some quarterly webinars in 2020. Those will be coming up on the schedule as they become available. We also have some short course programs. We currently have a short course program at our ICMCTF 2020 program in San Diego in April. That registration is available now if you go to the AVS short course website. We have the AVS New Mexico chapter, which will have a program in May. That schedule and registration is still being determined, but should open up in the spring of 2020. And as per usual, we have a larger short course program at the AVS International Symposium and Exhibition. And in 2020, that'll take place in Denver, Colorado in October. That schedule will be available during the summertime. And then we also have some upcoming technical meetings. And we have one coming up this January. If you haven't signed up, early registration is tomorrow, but we'll take registration after that. That is our PCSI meeting, Conference on Physics and Chemistry of Surfaces and Interfaces. That'll be in Boulder, Colorado. And as I mentioned, the ICMCTF program, or International Conference on Metallurgical Coatings and Thin Films, will be in April in San Diego. That registration is also available now. And then we have an upcoming ALD-ALE conference in 2020 that will be taking place June 26th through July 1st in Ghent, Belgium. That registration will be opening soon. And finally, we have a PACSURF 2020 conference taking place in Waikoloa Beach, Hawaii next December, right around this time frame. And details on that will be available on the AVS website as we get closer. So right now, I would like to introduce Gerardo Brucker. He's with MKS, and he's going to begin the presentation on high vacuum workflows. Thank you very much, and welcome, Gerardo. That will turn it over to you now. Thank you.
Okay, thank you. I hope everybody can hear me fine. I wanted to share with you like the overall plan for the next few hours. I guess you're stuck with me whether you like it or not. This is kind of what we're going to do. Kind of broke these down into 4 blocks, and just like Heather was saying, we are starting right now. I'm using the Eastern times here, but you know, everybody can do their own math for the time. We're going to do we're going to go in 50-minute blocks with 10 minutes breaks at the end. Coming back from those 10-minute breaks, we'll do a 5-minute, depending on the questions that we have, we'll do about a 5-minute answering questions. You know, we'll pick from whatever it is I get. I have the Q&A box open here. And then for the very last block, you know, coming back, I'll do the first 5 minutes, and depending on how things go, if there are lingering questions at the end or I get more questions along the way, we'll do the last 10 minutes of Q&A. And of course, this is just a a layout here of what we're going to do. As I always tell everybody here at work, it's always the best laid out plans that fail. So we'll try to stick to it, but we'll see where all this takes us. The audience itself will kind of guide us as we go along, and if I can see that there are certain themes, I might adjust course as I go. So anyways, again, following Heather's introduction, I'm Gerardo Brucker. I'm a Chief Technology Officer for Pressure and Vacuum Measurement Solutions at MKS Instruments. I am doing this actually from our building here in Longmont, Colorado, and I'm providing you here a couple contact points. You're free to call me, you're free to email me with any questions following these. I welcome questions. This is kind of how I learn and how I correct the course. Full disclosure, this is our first run at this course, this particular short course. So I expect that I'm going to have a lot of questions. I expect that I'm going to learn a lot. And, as time goes by, there will be tweaks to it. And so, please help me get better at this. This will, as always, in education, right? This is a continuous improvement process, as it should be in vacuum as well. All right, so just to give you a little bit of background, why is it that I'm doing these things and that I think I could be doing these things. I'm going to give you a little bit of my background. My vacuum experience started at Stanford Research Systems. I worked there until from 1990 to 2005. I was a founder and the product manager for their vacuum analytical instruments division. So I did a lot of vacuum product development there, including residual gas analyzers, ion gauge controllers. We did coarse crystal microbalances, a bunch of fun stuff. And that's what got me really heavy into understanding mass spectrometry and understanding gauging for vacuum, which is what I do today. That's my main specialty. From there, I moved on to Grumble Phillips Product Center here back in Colorado, where I went to college. And I worked on that between 2005 and 2014, when finally around June of 2014, MKS acquired Grumble Phillips from the division from Brooks Automation, and I have been a CTO for MKS since then. My focus, we have about 15 different CTOs right now because we have such a wide range of products. My specialty is pressure, and I deal with both the direct pressure measurement, which is all the baratrons, which we'll be talking about later, as well as the indirect pressure measurement, things like ion gauges and Pirani gauges. And just to give you a sense where I'm calling from, I'm transmitting all these or webcasting all these from our beautiful Longmont, Colorado. This was actually a view. It doesn't look as pretty today. This was the view yesterday morning going to work. This is what I see every morning. And I'm looking out the window right now. It's not looking as good, but certainly ready to start. So let's talk a little bit about the course. My objective today is to provide you a very comprehensive set of best-known practices for high vacuum system design and operation. My goal is talk about vacuum practices, talk about vacuum principles, vacuum system design and operation, with the goal of allowing you or helping you to optimize the capacity, the yield, and the overall throughput of your vacuum processes, which require an initial pump down to high vacuum. So I'm going to be a little biased today. I'm really going to be focused on vacuum processes. And by vacuum process, I mean either an industrial application where, you're making things so you can make money, or research applications where you're just trying to learn new things that you didn't know before. In both cases, these are vacuum processes that you have to run through. And my goal is to provide you some tricks and things that I've learned how to do over the last, too many years that I've been doing this, and that help me on a daily basis to make sure that all our processes, both in my R&D lab as well as in our production floor, are more efficient. I'll give you a couple of ground rules. I'm probably already doing it. I tend to talk a little too fast. If I get too fast, send me a note on the Q&A, say, you're getting out of control. I have this problem where as I run out of time, I talk faster and faster, and it becomes kind of counterproductive. I'm also going to tell you right now, if you ask me a question and I do not know the answer, I will not make up the answer, but I will certainly research it. I'll try to get back to you with an answer. You will notice as we go through the presentation, and I don't know if you downloaded it already, you're certainly welcome to do that and keep a copy of that. Some of the slides are a little heavy. My plan is not to go through all of that in every slide. We would never get out of here. My goal was for you to have those slides so you can always go back to them for reference. And the other thing you're going to notice is I do believe in the power of repetition, so don't get mad at me or annoyed at me if I repeat a few concepts a few times, maybe too many times. But I believe this is the way to walk out of a place, out of a session like this with some of the basic ideas just drilling into your head. And you will also notice as the course proceeds today, I will skip many of the slides as I move through the material. I'm not going to go through all of them either. And the reason I put them there is because I want you to have them so you can go back to them and refer to them in the future. Very often what I'll do is I'll get to a bunch of slides. I say, okay, there are all these slides here on these. I'm not going to go through them, but if you ever need something like this, you know where to go and get this information. And some of them, too, will give you a little bit of an insight into some of the other courses that are offered by AVS. For example, I teach a partial pressure analysis class. And so I introduced a lot of the slides that I used there in this presentation. I'm not going to go through them, but you'll get a sense of what it is that you will be exposed if you took that class as well. All right, we're doing good in time. I'm happy with this. What I wanted to do, too, before we get too far away and I forget, is to give you a little bit of my favorite bibliography. I kind of look at all of these that I do as I go through life and I learn all these tricks. I like to kind of, make a compendium of all the things that I know and then start sharing with people. And one of the things that I like to share with people are my favorite books. And this is my short list. This is a very short list, but it's very powerful and very appropriate for this idea of optimizing or getting the most out of your vacuum processes. So the first book, and I love this book, I think it should be on everybody's shelf, is Building Scientific Apparatus by John Moore. If you read the vacuum section in that book, that's all you literally need to know to start building vacuum systems and start being productive in vacuum. Plus, it will give you all the other information that you need for the lab, including electronics and principles of optics, ion optics, and so on. My second favorite book, this is my Bible, is by John Yates, Experimental Innovations in Surface Science. There's a second edition that came out, luckily, before John Yates unfortunately passed away, but here you have it. He was able to leave us a second version of what I consider to be one of the greatest books on tricks to use in your vacuum system, from building your own leak valves to, how to do internal heating to, moving stuff inside vacuum systems. He did it all. And my third book on general vacuum is Understanding Modern Vacuum Technology by Steve Borichevsky. This was just done in 2016. Poor Steve got this crazy idea to write a modern version vacuum book. I know from talking to him many times he regretted it later on, but he finished it, and I highly recommend this publication. After that, you have 3 references on mass spectrometry or residual gas analysis. We're going to be talking a lot about gas analysis today, so I consider gas analysis to be critical to being able to understand what's going on in your vacuum system and to be proactive about possible problems in your vacuum system. So here's my 3 favorite books. One of them is, of course, the AVS monograph by Drinkwan and Lichtman. I give this book to everybody that joins here at work. If you're interested in quadrupoles, how they really work, Dawson's book is great. And then a quick article, How to Use an RGA, where I provide a lot of useful information on kind of the usual and not so expected uses of RGAs. And finally, a link to the NIST Spectral Library. We'll talk a little bit more about that later, but this is very, very important link to have if you do any sort of mass spec analysis, and I hope you will consider that essential at the end of this talk. This is the website that you need to go to do spectral interpretation. Okay, so let's start. The first thing that I want to do is just kind of give you a little bit of before I do that, I wanted to go through this, some of the list of items that we're going to go through. I'm going to start talking about the physicochemical factors limiting the ultimate pressure levels in high vacuum systems. So I'm going to talk a little bit about vacuum in general, and we're going to talk about what is it that makes vacuum systems click, and what is it that limits the pressure, the minimum pressure that you can achieve, what I call the ultimate pressure in a vacuum system. We're going to be talking about two very important concepts, which are base pressure and ultimate pressure. These are two very different parameters that are critical to anybody's vacuum process. Base pressure, we're going to be talking about, which is a vacuum process related parameter. It has nothing to do with the vacuum system itself. It has everything to do with your process. It's a pressure you chose for your individual process. We're going to talk about selection rules for those base pressures. How would you go about selecting the best possible value? Then we're going to be talking about ultimate pressure, which is indeed a vacuum system related variable, and how ultimate pressure selection for your vacuum system then drives the vacuum system design. Once we have the concepts of base pressure and ultimate pressure, we're going to be talking about vacuum system design. I'm going to introduce the concept of vacuum system as an instrument, which is the way I go about doing vacuum system design in our R&D lab, and that we are presently also deploying to our production floor as well here at MKS. Then we're going to talk about gauging. Gauging is critical to vacuum processes. If you don't know your pressures, you're going to waste a lot of time, you're going to waste a lot of money in your process. So we're going to talk about total pressure measurement options. Then we're going to move on to partial pressure measurement options. We're going to talk about why partial pressure measurement in your systems is critical, why is it important to be able to do quick diagnosis. So we're going to spend some time on that. We're going to talk about leak detection methodologies and best known practices. I'm going to give you my own take on how to do leak detection. And finally, my favorite subject, we're going to get on block 4. We get heavy into, once we have all the basics, we're going to get into proactive pump down monitoring, what I call my methodology of follow the water in your vacuum system. And we're going to talk about how to use that to be proactive in your vacuum system and avoid delays, particularly during pump downs. I hope that makes sense. Okay, so starting with vacuum, we're going to level the field here a little bit. So when we talk about vacuum, vacuum is an enclosed space from which matter, generally air, right? That's what you start with in your chamber, has been partially or completely removed so that the gas remaining in the space exerts less pressure on the internal walls than the atmosphere. So you can kind of see the animation here. I'm taking the gas away. And so we end up with a few gas molecules inside this chamber. The pressure on the outside is higher than the pressure on the inside. And of course, vacuum technology refers to all those processes and all those physical measurements that are carried out under the vacuum pressure conditions. Vacuum, as we know, is everywhere. It's an integral part of the many products and processes we use in our daily lives. Everything we touch pretty much today is touched by vacuum, anywhere from the components in your cell phone to the glass on your cell phone to the coatings on, on your coffee mug. Everything today is vacuum related. Vacuum, as we know, is used extensively in manufacturing. Lots of these is thin film coatings, though as you well know, for example, in the semiconductor industry, there's a lot of other applications as well. But, as I always say, anywhere from microprocessors to plastic Buddhas, vacuum is used. Vacuum is also used in science. You know, we use vacuum technology to carry experiments, you know, surface science experiments, space simulation studies. Many things that are sent out to space need to be tested under vacuum because that's what's going on in outer space. So big chambers are developed for that, and of course, high energy physics. So the question is, as we start doing this, is why create a vacuum, right? We're all here because we work on vacuum processes, but I don't know how many of you ask yourself every now and then is, why do I need vacuum? Could I do my process without pulling a vacuum? Would there be, what if I didn't have the ability to create a vacuum? Could I still do the things that I have to do without having to pull a vacuum? And I'm sure that in most of your cases, the answer is going to be, no, I can't. And what I want to do now is address a little bit why it is that you can't. Well, this is why, because when you create a vacuum, your goal is to remove undesirable molecules from this chamber that you're going to be working inside and to create a controlled physical-chemical environment inside that vacuum chamber. And the motivation for you is to control the chemical composition of the gas and also, or control the physical properties of that gas. And the application, of course, is either perform a scientific experiment, you're trying to gain some knowledge, or you're trying to complete a vacuum process, you're trying to do some manufacturing, you're trying to make some money. So vacuum generation by itself provides the ability to monitor and control the physical chemical properties of the gas environment in which your process is going to occur. Sometimes you pull a vacuum because you want to control things like a mechanical force. You know, how much force is being exerted on a membrane, for example, or how much gas flow you're going to have from a chamber to another, or you're trying to do gas dosing, or you're trying to do a dilution of gas, you're trying to do an expansion, or you're trying to get your gases in your environment to start behaving according to an ideal gas behavior. Sometimes you pull a vacuum because you're trying to control the molecular density of your gas. In that case, what you might be trying to do is control things like evaporation rates, reaction rates, and so on. This is when we start getting into the physical chemistry of vacuum. Sometimes you're pulling a vacuum because you're trying to control the mean free path or the collision frequency between molecules. So, for example, you might be pulling a vacuum because you need to put your gas in the molecular flow regime, or you want to get it in the transition regime because you need to know what the gas is going to do as it's flowing through the system. Sometimes you do it because you need to store or transport ions through that environment. Perfect example is a particle accelerator, right, or high energy physics, where you need to transmit charged particles over long distances, you know, kilometers, and the only way that can happen is if you remove all gas, so there are no collisions with those ions or those electrons as they're going through the path. It might also be that you're trying to pull insulation, right? You're trying to create insulation, so you're trying to remove gas molecules from transfer heat from the outside, from the ambient, to your particular experiment. You might also be trying to do avoid surface collisions by reducing the amount of gas in your chamber and introducing a fresh sample or a fresh surface into a vacuum system. You can actually control the coating rate for those surfaces, the coating uniformity for those surfaces, how much heat transfer happens from that surface to the gas environment. You can, again, provide thermal insulation, and you can, of course, control the substrate purity ultimately. And, of course, by pulling a vacuum and controlling exactly what your gas is, you know, at pump down and then later on when you start introducing your own gases, what you're also doing is controlling the chemical reactivity in your system. So all of these are different reasons why you actually pull a vacuum. Some of you might be doing it for a variety of these. Some of you might be doing this of one of them. But these are the reasons why you need vacuum. And very often, when these are the reasons, vacuum is the only way to do it, so we are stuck with it. So what we are here to do today is to figure out how to make this process of creating this vacuum and doing these experiments as efficient as possible. So basically, improve your vacuum workflow. The other thing, too, that I wanted to touch on very quickly is pressure range in vacuum. This is one of my favorite slides to do, which is I'm going to take that chamber. Let's just say that that chamber is at atmospheric pressure, is filled with gas at atmospheric pressure, 760 millimeters of mercury. That chamber is 22.4 liters in volume. Then we know, if we took chemistry PChem 101, we know we have about a mole of gas in there, and we have about Avogadro's number of molecules, which means that we have more than 10 to the 23rd molecules in that system. What it means is that as I start pulling gas out of this chamber, I can divide that pressure by 10 or reduce it by a decade 23 times before I get to 6 molecules in that chamber. What that really means is that as I'm moving towards vacuum, I have many decades of pressure that I can cover. And that brings us to the next slide, which covers the typical ranges of pressure that you have in a vacuum system. So if you go from, starting at the top, go from left to right, you can see pressure dropping. Starting again on the left, going down, you can see different figures of merit for vacuum. You can actually see the 3 of the parameters that we're talking about that are controlled by change to the pressure, which are molecular density, mean free path, and surface collisions. And I love this table because it kind of gives you a sense of really why people work in different vacuum conditions, right? Here's a good example. For example, if you're trying to control the molecular density in your system, if you're at atmosphere at 760 millimeters of mercury, you're looking at about 10 to the 19th molecules per cubic centimeter of gas. You're trying to make a reaction go fast, this is the way to do it. If you're trying to slow it down, as you start moving over to the right, you can get, by the time you get to UHV conditions, 10 to the minus 9 to 10 minus 9 torr, say, you have about 30 million molecules per cubic centimeter. And eventually, as you get down into the minus 12s, which is extreme high vacuum, you have about 32,000 molecules per centimeter. This is how you control molecular density. You control chemical reactions, evaporation rates, and so on. On the other hand, if you're in an accelerator, and you're a particle physics guy and you're trying to send a molecule down a tube that is about, is a few kilometers long, you can see the mean free path between collisions here only gets to match the kilometer range by the time you get down to 10 minus 9 torr. You can see it right there in the middle, the 51 kilometer mean free path. That's awesome. That means that for a particle physics guy, this is why typically they're operating to 10 minus 9 torr. That is the place where the protons, the electrons, whatever it is, they're flowing down their tubes, right, are going to be able to go collision-free for long distances and get accelerated to the insane amounts of velocities that they achieve. And the final one, which is also very interesting, is if you're a surface scientist and you just clean a surface and you need to run an experiment, if you were doing this at atmospheric pressure and you were you just finished cleaning up your surface, it would take about 3 nanoseconds for that surface to be coated with atmospheric gas, with a monolayer of atmospheric gas. So you would, unless you are capable of finishing that experiment in 3 nanoseconds, right, you're really going to have to do something else to be able to finish. But what you can actually see is that as you go further, lower and lower in pressure, particularly as you get down to 10 to the minus 9 torr, now your time to create a monolayer of gas on these systems comes down to about 38 minutes. So that means that now, if you introduce a sample into a vacuum system that is at UHV conditions, 10 to the minus 9 and under, and you clean that surface, for example, argon bombardment on the surface, you get a pristine surface. Now you have at least 38 minutes to complete your experiment. So you might be able to do it now. And if you go further down, by the time you get to the extreme high vacuum conditions, which are achievable today, you will have 27 days to complete your experiments before that surface gets coated. So what I was trying to do here is kind of go through, remind ourselves why is it that we do this crazy thing, this vacuum thing that is so time consuming and that sometimes we are slaves of. And that we really don't have any other way to do it, other than to live with it. So what I wanted to do next is now we're going to start going down the path of the building blocks of a vacuum system. And this is kind of how I'm going to do all of it moving forward. A standard vacuum system can be broken down into 4 basic building blocks. We have the gas containment chamber. We have pumps. We have a pressure, so we have the gas containment system. We have the pumps. We have the pressure measurement system. And then we have a gas introduction valve to allow gas into the system once we are ready to start the process. Vacuum generation, of course, requires very dedicated vacuum equipment and instrumentation that is specifically designed to generate, monitor, and control low pressure conditions in that enclosed volume. And what is and this is going to be key throughout the rest of the presentations, the gas pressures that is established in that vacuum chamber are the result of a dynamic equilibrium. And I don't know how many of you go around thinking about the dynamic equilibrium that is going on inside your vacuum systems, but I'm here to tell you that if you keep this in mind every day, this is going to make your life a lot easier, and it's going to help you solve a lot of problems. But so this dynamic equilibrium I'm talking about is between the flow of gas molecules that are allowed into the chamber due to a variety of reasons, and a counteracting flow of molecules that are driven out of the same chamber by the pumping station. The idea then is we have this balance between molecules going in and molecules going out, and which are again pulled out by the pumping system. The pressure that you get is always going to be the balance between the two. It's the ratio between what's going in divided by what's being taken out. And this dynamic pressure control, of course, provides the opportunity to achieve consistent and stable vacuum conditions. So let's look at this with the pressure equilibrium equation, and I'm going to be using this a lot. So this one is one you kind of want to shut down on a piece of paper as we're talking. So vacuum is a dynamic equilibrium state in which gas molecules flow in and out of the chamber. The pressure in the chamber is a balance between what goes in, Q, I call that the molecular flow rate into the chamber, divided by S, which is the pumping speed of the system, the molecular flow rate out of the vacuum system. And you might say, well, no big deal, we all know this. This is something you've got to remember a lot because Q, as we're going to see, has a lot of different sources. And you've got to keep them all in mind. And as long as you keep this equation in mind, you will always be able to make this balance or work on this balance between, to be able to achieve lower pressures. Do I lower Q or do I increase S to make my pressure smaller in my system? So remember that equation. This is going to come back. So as we talk about vacuum, right, I don't know about you, but I know there are some cases where people will seal, particularly surface science, people will seal their vacuum systems. They'll start a pump down, and they'll do their pump down, and then you will have to basically kidnap their children for them to ever want to open up that vacuum system again. But with the exception of those people, for most regular users, what you'll see is that all vacuum systems, all vacuum processes start with an initial pump down from atmosphere. So you have a bunch of items or a bunch of substrates, a bunch of samples, your experimental subjects that you have, your designs, your devices under test, your plastic Buddhas that you're going to coat, whatever it is, you're going to put them inside your chamber, and you're going to go ahead and close the door, and you're going to start a pump down. And the process is going to start, the system is going to pump down. You can actually see it right here, right, your atmosphere. You load your samples right here. The process is going to start, and the pump down is going to start, and your process will start when you hit a base pressure. This base pressure is a target that you actually set, and that is specific for your process or your experiment, and that you're going to say, well, when I hit this pressure, I am going to be able to start my process or my experiment. It's your decision. It's linked to your process. Of course, if you continue the system, if you continue pumping on this system after your base pressure achieved, this vacuum system would continue to pump out even further, and it would ultimately achieve what we call the ultimate pressure. And the first thing that I want you to keep in mind is that these two numbers, these two parameters, base pressure and ultimate pressure, and I hope this is true for your vacuum system today, should never be the same. And we're going to be talking about this a lot. In a properly designed vacuum station, the ultimate pressure should always be lower than the targeted base pressure for your vacuum system. Okay, next one. So that's what I'm saying. And a very good rule of thumb is to make sure that your base pressure is greater than at least 10 times the ultimate pressure which your system can achieve. And I'm going to talk about why all this is the case. So let's talk about what happens during a pump down. As you load your samples, again, we are atmospheric pressure. We load the samples right here at the top, and we start the pump down. The first thing that happens is the pressure drops very, very quickly because we are pulling out the bulk of the gas out of the chamber. Usually you do this with your roughing pumps. You might or might not be exposed to your turbo pump at this point, but the bulk of the gas goes out. Then eventually your turbo pump or your cryo pump or whatever it is you use, your ion pump, is exposed to the gas. And now you move on to this other regime where all the bulk gas has been removed. And now the gas that you're removing is basically loosely bound water molecules that are coming off the walls of the vacuum system. At this point, which is kind of what I describe as 2, the pressure in the system is dominated by water. And the pressure is dropping because the outgassing rate of the water molecules is decreasing as the loosely bound water molecules start to go, outgas from the walls, and we get closer and closer to the walls. And the water molecules that are left, which are now closer to the walls, have higher binding energy and outgas at a much lower rate. So as this happens, right, the bulk went away, then I start pumping on the loosely bound molecules. I get closer and closer to the walls. Now the gas molecules, the water molecules are tightly bound to the vacuum system walls, and they start outgassing very slowly. And very slowly I start achieving the ultimate pressure in this vacuum system. By the time I get to this ultimate pressure right here, what I basically left is with tightly bound water molecules, right? I have which are outgassing very slowly, and the gas composition here at this point is really a combination of those tightly bound water molecules outgassing into the chamber, backstreaming gases, and any contaminants that might come in through things like permeation, backstreaming from the pumps, and so on. So, but the important point to make here is that you will eventually get to a point where outgassing water is very small. It's no longer the major contributor to the vacuum system. Now you have a combination of gases in the chamber, right, that it's not going to change the pressure of that system very quickly. Particularly if you don't outgas your system, you don't bake out your system routinely, what you're going to find out is that this ultimate pressure will be very repeatable from day to day, unless you start developing leaks and so on in your system. We'll talk about that. But it's pretty much a number that you get to after a long, long pump down and you get stuck with. Okay? So remember, you start your process at base pressure, all right? Your system eventually will go to ultimate pressure. I am hoping that today you're not operating your experiments when ultimate pressure is reached. So let's talk a little bit about base pressure. Base pressure is a key process specification. It's linked to your process, not to the vacuum system. The base pressure target is selected by you and optimized to assure the cleanliness of the internal chamber components and the precise composition of the gases flowing into the chamber during the vacuum process. You got to choose this one very wisely. You want it to be small enough that when you introduce your gases, your process gases, they are not contaminated by whatever was left in the chamber. But you don't want it to be too small because otherwise you're going to be waiting forever. And that's going to cost you time and money. Which is what we are trying to save here, right? We're trying to be as efficient as possible. So there is this yin and yang, right? I want it to be as high as possible so I get there as quickly as I can, but I also want it to be as low as possible so I have a clean starting condition, I have clean vacuum environment, I have clean vacuum walls. Okay? So base pressure is a process specification, not a vacuum system specification. The pump down in your system is completed when the target base pressure is achieved. At that time, the process can start. The pump down time to the base pressure is generally a very significant contributor to the overall process time. It directly affects throughput and bottom line. Over my career helping people, with vacuum systems, I've seen thousands and thousands of chambers. And I'm sure that I asked many of you, what is it that you worry about most, when you start a process? Pump down is always top of the list, or high in the Pareto chart of problems. You worry about leaks. You worry about things that are going to delay that pump down. So pump down time is a very important parameter. And pump down time is to base pressure, not to ultimate pressure that we're talking about here. What we are looking for is always pump down times that are short and are repeatable. And what I'm going to tell you today is I hope that all of you are tracking those pump downs today. And the other thing that we're going to go through today, we're going to go through some gauging. I cannot emphasize enough how important it is during pump downs to have accurate and repeatable pressure gauging, which is essential for an efficient pump down. If your gauge reaches too high, you're going to be waiting too long, right? And you're going to waste time before you achieve your targeted base pressure. If your gauge is read too low and you think that you're a lower pressure than you really are and you start your process, your yields might go out the window. So your gauges have to be good. You have to be accurate, they have to be stable, repeatable, and they have to be maintained. Okay? Ultimate pressure, on the other hand, is a key high vacuum specification, high vacuum system specification. The ultimate pressure depends on your vacuum system design and component selection. It's not dependent on your process. You choose how you're going to build your vacuum system to achieve an ultimate pressure that hopefully is going to be about 10 times lower than your base pressure. And I'm going to show you why you want to do that. The pump down time to ultimate pressure is influenced a lot by system history, and it's not going to be repeatable run to run. You do not want to rely on achieving ultimate pressure to start, repeatably every day to start your process. So, I want to say one more time, target base pressure for your process should not equal the ultimate pressure on your vacuum system. So, this is my first rule here. That's a vacuum system designed for pump down. For your process, you select your base pressure, which is a target that provides the required yields for your vacuum process. You might know what that is up front. You might not. You can always test it on a chamber and see what you get. Once you know your target base pressure, you define the ultimate base pressure for your vacuum system, and you want that to be at least 10 times lower than your base pressure. Based on that, once you know what that ultimate pressure needs to be, you can either design a fresh vacuum system to meet that ultimate pressure, and we're going to talk about how you do that, or you want to modify your vacuum system so that you can achieve those ultimate pressures. That includes selection of pumping station, gauges, sealing materials, and so on, and we'll talk a little bit about that. So in all cases, you will start your vacuum process as soon as the base pressure is achieved. So here is why you want to do pump downs to base pressure and not to ultimate pressure. When you're doing pump downs to base pressure, your pump downs are shorter, they are repeatable, and you have immunity against changes in sample cleanliness, dryness, and even development of small leaks in the system. You can see it right here. The blue line is your typical pump down, right, in your vacuum system. Again, you start here at base pressure, and in this case, the system is in good conditions, and it will achieve its base pressure. But in the red line, I show a case where, for example, your samples you introduce are a little more wet this time. Or maybe you have a leak in your system. So what's going to happen in this case? You're not going to be able to achieve that ultimate pressure. Basically, your grad students or your operators, your tool operators are going to come to you and say, hey, boss, I cannot pump down my system. I cannot start. That's because, in this case, if your ultimate pressure is never being reached. So if you make your ultimate pressure the start for your process, you are in big trouble. On the other hand, if you selected the start for your process as a base pressure before ultimate pressure needs to be achieved, you can actually see that now you can still start, and there will be very little difference between the time when the system was in pristine initial conditions to where later on things change, due to a variety of possibilities. So this is how pump down to base pressure is going to save you a lot of time. Your job is to track these times, right? Track down these pump downs to base pressure. So looking for sudden increases, right, in pump down times, and looking for or systematic increases in pump down time that might require you to go survey your system. The bottom line is what is happening here, and the reason why you get away with this, even if your system, right, develops an air leak or starts getting contaminations I'm showing you here, is what you're basically doing by selecting a base pressure that is higher than the ultimate pressure is you are allowing a buffer of water to be removed from the chamber so that you can still achieve your target base pressure. So basically what's happening here is that you had to pump down for a longer amount of time, and what you were doing during that time is you were forced to remove more water from the walls so you have lower outgassing and make up for the extra gas that is coming in the way of an air leak or contamination into the system. And again, pump down to ultimate pressure. If you're really relying on ultimate pressure of your system to achieve, to start your process, you're going to be looking at long pump down times, very unpredictable pump down times, and you're going to be very, very dependent on changes in sample cleanliness, dryness, and even the development of small leaks. You can actually see it right here. If this is my start dry, right? I'm going to do this again. If this is my start dry, this system will never start. You will have lots of frequent no starts if leaks or contaminations develop in your system. Okay? The reason why this is because if you're always relying on pump down to ultimate pressure, you're basically not giving yourself a water outgassing buffer in your system. So there is nothing else to remove from the walls. If you have a leak, you're going to be under the influence of that leak, and there is nowhere else to go. Okay? All right, so I'm going to spend the last few minutes here. We are doing pretty good, actually. Talking a little about ultimate pressure, and because then after that we're going to go into vacuum system design. But what I wanted to do is talk a little about Q, right, into the system. And we all know that it doesn't matter what chamber you have, if you can pump on that chamber as hard as you want, you will never achieve zero pressure, right? P is never zero. The reason P is never zero is because of two reasons. S will never be infinity. Remember Q over S? And Q will never be zero. And Q will never be zero because there are lots of sources for Q. There are leaks, there are permeation, there is desorption, diffusion, outgassing, backstreaming from the pumps, vaporization, right, of material that might be left in the chamber. There is even particulate that might have gone into the chamber that is outgassing. And of course, the dreaded and mythical virtual leaks. So in a typical vacuum system, so you actually, going back to the previous slide, you can actually see, right, every one of these blue items there is a source of gas can flow into the vacuum system that contributes to Q. So we go down, the ultimate vacuum pressure in a system is going to be an equilibrium between the gas load and the vacuum and the pumping speed performance, right? So the ultimate pressure in your system is going to be a balance between stuff coming in through leaks, stuff outgassing, mostly water. Remember, by ultimate pressure, it's all tightly bound water molecules that are going to outgas really slowly, and they are, the amount of them on the wall is not going to change very, very quickly. So that Q outgas of water is going to remain the same for a long time. It could also be any contaminants that came in with a sample. And of course, you also have to worry about permeation. So the ultimate pressure is going to be the ratio between what's going in, the Q leak, Q outgas, and Q permeation divided by the pumping speed. Of course, Q outgas in a typical vacuum system, a clean vacuum system, is going to be dominated by the tightly bound water. And if you're in your life every day, you rely on your vacuum system to achieve ultimate pressure to start your process, what you're doing every day is you're waiting for literally all the water in the system to go out and just get to the last few layers of water left on the walls to outgas, in which case, if a leak develops or permeation develops or additional contaminant comes in with your samples, you have absolutely no buffer in your gas to achieve the ultimate base pressure that you were achieving yesterday. And that process will now, you will now be able to start it that day, which is why I'm so adamant about these two concepts of base pressure, which is a process linked parameter, pump down times to base pressure. You got to track them. You got to know what they are day to day and look for any changes in them. And then you also design your vacuum system for what is going to be your selected ultimate pressure, which should be at least 10 times lower than your base pressure. And I've given this presentation many times, and every single time I have people coming up to me and going like, oh boy, what you're saying that I shouldn't do is exactly what I'm doing every day. I'm going to have to go and rethink some of these things. And I hope that these will trigger exactly the same thoughts for you. So anyways, we are here at 11:50. I hope you were able to stay with me through this first block. As we move on to the next one, I'm going to answer some questions if there are any. And then after that, we're going to now move on to vacuum system design, now that you know how to select your base pressure and your ultimate pressure. All right, we'll see you in 10 minutes. Very good. I can see recording started. Excellent. This is a slide we left in. I do not see any questions. I don't know if there is anything there that we need to address at this point.
There are a couple of questions, Gerardo. You might need to expand your screen on the Q&A.
Really?
There's from Rodrigo Guzman Mosqueda and Mark Lee.
Huh.
Can you view them? If not, I can read them to you.
Oh. No, I don't. Oh, there we go. Oh, yeah. Okay, now I see it. Okay, sorry about that. Okay, so somebody's asking, was it possible to get a copy of the slide deck? There is one, right, Heather?
Scroll further down. We answered those questions already. If you scroll all the way down to the bottom, you may need to expand the Q&A box itself.
I see it. Okay, so two of them. I see them. Rodrigo and then Mark Lee. Okay.
Correct.
So when you say baseline pressure selection affects the yields, does it mean in general that at higher base pressure variation in the process may cause your product to go out of specification in some way? Yes. So here's how I look at base pressure. The idea is, why do we even bother, right? Pumping out a system to then fill it up with gas again. You know, it's kind of a funny deal, right? You look at a lot of repetitive processes, particularly in the semiconductor industry, right? They will load a bunch of wafers into a chamber, fill the chamber with argon, right? Fire up a plasma, do a deposition, and then remove the wafers, and then pump down in between, only to fill the chamber again with the same argon gas. And this gets done again and again and again, right? And you might say, well, why do you bother pumping in between to a base pressure when in reality, all you're doing is just always having argon in that system? Well, that's because every time that the plasma fires up and the deposition takes place, contaminants can come out in the chamber, and now you don't exactly know what the composition of your gases is going to be. So when you load samples in your vacuum system for, starting from atmosphere and you pump down, what you're really trying to do is you're trying to say, what is the highest pressure of residual gas, what's left in the chamber that I can have, so that when I introduce my process gas, right, that residual gas that was left in the chamber is not going to affect my yields. So I'll give you a perfect example. If you're doing an aluminum thin film deposition where oxygen levels could be a problem, what you're going to have to ask yourself is, what are you going to do? You're going to pump out the chamber, right? You're going to go to a specified base pressure. Then you're going to go add some argon into the chamber. That argon is going to mix with whatever was left in that chamber. And now you're going to fire up the plasma, and you're going to do your aluminum, right, sputter deposition. Well, the question you have to ask yourself is, how much oxygen can I have in that chamber when I do my sputter deposition before the aluminum could start suffering oxidation? And those numbers are well known, right? So since you know how much argon you're putting in and you know how much oxygen you can take, you can then make a determination from the very beginning of how low you need to go with all your pumping, so that when you introduce the argon, there is no way that the residual levels represent more than that percentage that you can accept. So yes, the bottom line is that you choose your base pressure so that when you introduce the process gas, whatever was left in that chamber will not affect the yields of your process. And it could be for a variety of reasons. So I hope that answered the question. So it is true that a higher base pressure variation in the process may cause your product to go out of specification in some way. Yes, if you decide to start your process too early, for example, and you have a lot of water in your system now, which is typically what's going to happen. Let's say you were supposed to go down to a 10 to the minus 6 torr, but you say, okay, I don't have time to do that. I'm going to start at 10 to the minus 5 torr, and now you add a millitorr of gas. What you're doing now is you're saying, okay, I'm going to start with 1% of water in my argon gas versus the 0.1% of water that I will have in that place. Is that going to affect the quality of my coatings, the quality of my experiment, whatever it is? Very likely it will. So let's see. So they have another question. I think this one is pretty quick. I knew I said only 5 minutes, but I love questions, so there. So pumping process consists of pump down and ultimate vacuum pumping. Each time when we perform the experiments, would you suggest to start the ultimate vacuum pumping once the base pressure is achieved, or after a specific amount of time after pump down? I'm not sure I completely, each time when we perform the experiments, would you suggest to start the ultimate vacuum pumping once the base pressure achieved, or after? Okay, all right. I'm gonna give this a try. So this is the way I look at it. You pump down, you load your samples, you start pumping down, and what you do is you select what your base pressure is going to be. So in other words, at what pressure are you going to allow your process to start? What you also do is you, either by experience or by design of your vacuum system, you also set an expectation for what that pump down time is going to be. So every day, what you're going to do is before you start your process, you are going to go and wait until that base pressure is achieved. And every day you're going to write down what that number is. Every experiment that you do, and you're going to look for trends. You will not start your process until that base pressure is achieved, unless you have some reason to believe that you can, in which case I would choose a higher base pressure. And if you're not achieving that base pressure in the amount of time that, than you normally do, you can wait a little longer, as you move further towards ultimate pressure, and say to yourself, this is taking longer than usual. I should do something, right, soon to address, and we'll talk about what that means. I should do something to start servicing my system so I can go back to the original short and repeatable pump down times, right? in that system. Or maybe what you'll see is that you'll have a sudden change in the pump down time, right? Today it takes me suddenly forever to pump down, and it's taking me forever every day, in which case you might have developed a leak in your system, for example. But so the bottom line is, this is not a time thing, it's a pressure thing. You get to the pressure you want, you measure how long it took. If it was the usual time, within a certain amount of time that you allow yourself, it's all great. If it's starting to take longer or suddenly it takes a lot longer, it's time to start acting on your system. This is costing you time and money, and it's not going to get any better. And a lot of what we're going to be talking about on block 4 is how to identify that, block 3 and 4, how to identify that early before you wait several hours to say, hey, I never got to my base pressure. I wonder what's going on, okay? So I hope that answers those 2 questions. And we are going to move on. So we were on the ultimate pressure equilibrium equation, and what we said was, for a vacuum system that we just let pump down for a very, very long time, where we just pull out all the low-hanging fruit outgassing water molecules from the walls, right? The ultimate pressure is a combination of what's going in through leaks, outgas, and permeation mostly, and divided by the pumping speed of the system. And Q outgas, which is what I have there, I would guess that in 99% of your vacuum systems is going to be the dominant species in that vacuum chamber. So moving down now. Oh, boy. There we go. So now we get into vacuum system design. So you selected the base pressure for your process. You selected the ultimate pressure for your vacuum system. How do we design the vacuum system? Well, as you know, there's a bunch of vacuum equipment out there you can choose from. There are all kinds of different pumps, but we're going to start from a high level. This is why I'm so adamant about this P equal Q over S. Once the ultimate pressure is specified, it is time to design the vacuum system. The first thing is we got to choose the pumping system. Obviously, since S is in the denominator, we're going to have the largest possible S value that we can afford. So when we build a vacuum system, pumps are always an issue, right? They're usually one of the most expensive parts of your vacuum system. What you always want to do is you want to buy as much pumping speed as you can. You want to make S as large as you possibly can. You also, on the other hand, now you made the denominator, right, big, you also want to work towards making your numerator small. And so as far as chamber design, you want to minimize the amount of permeation into the chamber by the proper choice of leaks, right, of seals, and so on. You want to minimize the amount of outgassing by selecting the proper construction materials for your chamber and using the proper treatments for those materials, and we'll talk a little bit about that. You want to minimize the possibility of having leaks by choosing the proper sealing technology, right? So you want to minimize Q permeation by proper chamber design. You want to minimize Q outgas by choosing proper materials and treatments. You want to minimize Q leaks through the choice of proper sealing technology. And on top of that, as you do your vacuum system design, I cannot emphasize how important it is to know your pressure. And I'm not saying this because I make a living selling pressure gauges, but it's because there is a reason why we work so hard on making accurate pressure gauges here. And it's because accurate and repeatable pressure measurements are money for your process. So these are the guiding principles behind a vacuum system design. So we'll go a little bit through a table here. This kind of looks like the other one we did on the pressures. And this one kind of goes through all the different technologies that are used to address the different pressure levels. Again, as we move out here, right, as your ultimate pressure drops, right, it's going all the way from a system operating at atmosphere all the way to extreme high vacuum levels. So this is the pressure direction. In this side, we have vacuum chamber materials, pumping system selection, sealing technology, and gauging. And this is a top view, of the different technologies that are used. We're going to go into more detail into all these, particularly onto the gauging technology. But as you expect, if you're typically pumping down into the high vacuum, which would be somewhere around here, your vacuum chamber is going to be made out of metal. right? Stainless steel is a typical material that you use. It'll typically be electropolished. It will be baked, right, so that the amount of outgassing is very small. You'll use turbo pumps, cryo pumps, or ion pumps to do your pumping. And you'll have to use metal seals to avoid the permeation effects in your chamber. But see how as you're doing this, as you're choosing all these materials, you're thinking about all these cues, right? Choosing stainless steel, that will affect Q outgas. And you can actually go and look up what Q outgas is going to be for different materials. As you're choosing your pump, right, you're thinking S now. As you're choosing your metal seals, you're thinking Q leak. Of course, the chamber also, you're looking at permeation, right? And here you're looking at permeation as well with the seal. And finally, if you are in a high vacuum environment, as you have to choose the gauges, you would choose an ionization gauge. So pretty much this table gives you an overview of what the different pumping technologies are depending on what the pressure range which you're going to be at. And when you build a chamber, remember, you're building it for the ultimate pressure you selected. You're not, when you're building a system, you're not building it for the base pressure. Base pressure is your process number. All right, so moving forward, we'll talk a little about sealing technology. Vacuum seals are big contributors, right, to Q leak in our equation. Limited the ultimate pressure specification of vacuum system. The low to medium vacuum systems, you know, we all like to use O-ring seals, particularly systems that open and close a lot, right? We all use O-ring seals. With O-ring seals, look at everything you have to worry about. You got to worry about leak of air through the seal. You got to worry about diffusion of material through the of gases through the material, permeation of material from the atmospheric side. You have to worry outgassing from the surface of the O-ring. So the bottom line is, if you're going to be doing any sort of high vacuum work, which is what I believe the majority of you is doing today, what you're going to do is you're going to do metal seals. And common metal seal, of course, is conflat seals today with a copper gasket, right, with a knife edge seal. But there are lots of other technologies out today, like EVAC seals for KF flanges. There are now, these days, there are also the, what is called, the other rings, right, helicoflex seals that you can use that are still, they're fast to replace. They don't require all this complicated procedure to do a conflat seal, but provide a little bit, provide the permeability that we're looking for. And here I'm showing, right, typical metal-to-metal seal here. That is what you would typically use to eliminate all these problems of leaks, diffusion, permeation, and outgassing. So kind of continuing with the question that was asked earlier, right, do I go by time or do I go by base pressure? The problems, right, particularly with leaks, are a real issue in vacuum systems where you need to open up the chamber one or sometimes many times a day to produce something. So, for example, this is a big chamber where they do optical coatings, right? These chambers very often do, you know, maybe do a 4-hour run, and they'll run, you know, anywhere from 4 to 5 times a day, right? So, which means that this door with a big O-ring that is around it is going to be open at least, you know, at least in that case, you know, 4 or 5 times a day. So systems like these, coating chambers or even load locks for other chambers are the ones that you're going to have to be looking for, particularly for sudden changes in that pump down time that we were talking about. Or sometimes what you will see is you might see slow changes, slow increases in the pump down times to base pressure, which are caused by the slow accumulation of contaminants inside the chamber. You know, maybe as you introduce more substrates, those substrates bring contaminants with them. They start coating the inside surface of the wall. And like I said before, if if this starts building up slowly, what you're going to end up doing is taking a longer time to hit your base pressure, because what you're basically doing is waiting for more water to get out of the chamber before you hit your base pressure. And what you're literally doing is wasting time at that time. So, many people that are doing these sort of practices where you have a port that needs to be open, at least once a day or many times a day, many of them have leak checking practices that are very reactive. So in other words, what they'll do is they'll say, okay, I'm going to close my chamber, I'm going to cross my fingers, and I hope that everything goes well on this run. But sometimes it doesn't, so I'm going to be ready with my leak detector in case it doesn't pump down. What I'm going to be talking about later on in blocks 3 and 4 is how to avoid this trap where, you wait 2 hours for the system to pump down and it just never gets there, and now you wasted time, precious time you could have avoided originally. So we're going to be talking a lot about proactive leak checking technologies, right? What I call typically follow the water techniques, which will allow you to improve your throughput and eliminate these bottlenecks, right, due to slow pump downs. I have a slide here on virtual leaks. When you do a vacuum system design, particularly a chamber like that one that has a lot of internal structures that need to be fastened and so on, one of the things that you have to be very careful is virtual leaks, which is the release of trapped gases from small volumes with very low conductance path that can also contribute to Q leaks. So in other words, leaks don't only come from the atmosphere, but can also come from trapped gas inside the chamber. And a very common example is people bolting things to the inside of the chamber, and one of the things, or bad welds, right, non-vented screw holes and blind stud holes as well are big problems. What I recommend for these, of course, is TIG welding whenever you can to eliminate bad welds, vented screws, and slotted surfaces whenever you can for materials. In terms of outgassing, outgassing is a spontaneous release of gases and vapors from the chamber walls, right? They can be from the walls, from the elastomer seals, materials that you have inside, your own samples that you're loading into the system. This outgassing, of course, is highly dependent on what the gauge is, the chamber is made out of. It will be highly temperature dependent, so if the room temperature drops, you're going to find your outgassing drops. If the room temperature goes up, it will go up. And you might also find that these outgassing rates change with time, like particularly a chamber that you use routinely, day after day after day. You might actually find out that if you're careful, your pump down times actually get shorter because you start outgassing all the impurities that you started with. Typical sources of outgassing: water, hydrogen, synthetic oils and grease, residual solvents, fingerprints, cosmetics. The chamber that I showed you before, we have one of those in one of our optical groups here at MKS, and the guy actually walks into the chamber every day and has to put booties, around his boots. And you always have to hope that he remembers to do that every time. And of course, the way you mitigate outgassing is bake out the vacuum components, good vacuum practices, gloves, avoid organic solvent cleaning, and so on. So these slides are for you with some recommendations. So I cannot emphasize enough how important it is to, I'm going to take a quick peek, how important it is to when you design your chamber to keep outgassing in mind. It's not easy to throw pumping speed at a vacuum system because it's very expensive. Every liter per second of pumping speed is going to cost you a lot of money. So what you want to do is you want to throw as much effort as you can into the design of your vacuum system in minimizing Q, into minimizing the outgassing, the leaks, and so on that are going on inside the system. So I cannot emphasize enough paying very, very good attention to the outgassing characteristics of your chamber. So what I mean by this is, and I'll show you in this next slide what this is all about, is if you're going to design a chamber, model it. Maybe you're buying it from somebody else, then you don't get to do this, but you can always get the model. And so what you want to know is what are the wetted surface areas inside. You want to know what the materials inside this chamber are, how these materials were finished, and you want to know your chamber volume as well. All of these things will matter. So, you know, I know most of you will say, no, look, I just go whatever I got, I bought my chamber, and this is what it was. The reality is all of these things are negotiable, right, with your tool providers, and you can always dictate what you want. So if you work up front with your tool vendor, if you're not making your own, or if you work up front in your own design and you pay attention to these things, you can actually save yourself a lot of money on pumping by being careful on the selection of the materials, the selection of the surface areas, finishes, and chamber volume as well. So particularly important is the construction materials for your chamber. There are lots of tables that show that you can go and look and download from the internet that have outgassing rates for materials. And what I'm telling you is those outgassing rates are for ultimate pressure. So in other words, they will tell you this is the outgassing rate, the Q per square centimeter of stainless steel, for example, unbaked, or this is if it's baked, or this is if it's electropolished. So you can actually, if you know your surface area of your vacuum system, you can go and look up on tables how much Q you're going to have from that material, whether you are unbaked or you're baked, and that might allow you to choose a different material or different conditions for that material to be used in your chamber, reduce the Q, and save yourself some money on pumping speed. Okay? So when choosing the construction materials, you have to consult your published outgassing tables, and of course, other things come into play, like for example, the materials don't have to be compatible with the processes that you're trying to carry in your system. But it's not just about saying, okay, I want my chamber made out of stainless steel. You want to know, is it stainless steel 304, 316, 304L? Do magnetics matter, and so on? But we also want to be very well aware of the material treatments as well. And there are many, many ways to change the outgassing characteristic of surfaces, particularly stainless steel. Stainless steel could be aqueous clean before it's given to you. It could be plasma clean. You could plasma clean it every time. It could be electropolished. It could be vacuum fired. It could be anodized. It could be coated. It could have a titanium or aluminum oxide coating on it. It could be polished versus rough. All of these decisions affect the value of Q outgas in your chamber. And I cannot emphasize enough how important it is to understand those numbers. So here I'll give you a good example, right? If you look at unbaked stainless steel, for example, right, 10 hours of pumping. So if you take a stainless steel chamber, a stainless steel wall, unbaked, right, that chamber will outgas 10 to the minus 10, 3 times 10 to the 10 millibar per liter second to the minus 1 per square centimeter of wall. On the other hand, if you go ahead and you take that same system and you bake it out 150 C for 24 hours, that outgassing rate goes down by 2 decades to 10 to the minus 12. So what that means is that you could make a decision when you build your vacuum system. You could say, look, I don't have time to bake out. Then you're going to know you're looking at about 10 to the minus 10 millibar liter second, right, per square centimeter in that system. And you know what your surface area, you'll know your total outgassing, you'll be able to calculate what your pumping speed is. Or you might say, no, I'm going to go ahead and bake every time, and I'm going to buy a pump that has 2 decades less pumping speed and achieve the same ultimate pressure in my system. So I hope that kind of explains to you how this stuff works. Same thing for copper gaskets, right, and so on. There are numbers for outgassing for everything. Okay. So outgassing minimization. I'm a big fan of understanding outgassing in your chambers. 2 sources for outgassing, right? Vacuum chamber internal surfaces, and then there is all the devices, substrates, and components that are loaded into your vacuum system. Of course, clean and dry components should be loaded into your vacuum system. Start with clean and dry samples. So what I'm trying to say here is when you consider outgassing in your chamber too, you want to be cognizant of it's not only the outgassing of the, for ultimate pressure, it's important what the outgassing of your chamber is, right, of your system is. You also need to consider that you're going to bring other things into your system. There are also things that you're going to do in your system when you run. For example, if you're going to run a plasma process, during the time that that plasma is running, you are going to have energy being dissipated inside that system, and that energy will naturally increase the amount of outgassing into your chamber. So you might know what your ultimate pressure in that system is when the system has been pumped for a long time, and you completed your outgassing, but you have to consider the fact that the outgassing will increase when that plasma turns on. So you might need to consider that into your calculations as well. The best way, every time, the best way to reduce the internal water outgassing is to deliver energy into the walls, increase the temperature of the walls so that the rate of outgassing increases and the amount of molecules on the walls goes down. And so this includes things like heating jackets, internal infrared lights, internal UV lights, and the infamous, I cannot tell you how many times I have been at a place where we are standing there waiting for the system to pump down, right? And we've been there for the 2 hours, and I look at the operator, I go, hey, the 2 hours have just gone, and we're still not at base pressure. And I go, what are you going to do? And the operator will tell me, well, I think what I'm going to do is I'm going to start process, and then we're going to go see what happens, because very often the process itself will affect what the outgassing capabilities of the system is, because maybe what you're doing is coating the walls as well. So you can play tricks like that as well to improve the ultimate pressure of your vacuum system. And so going along the lines of these, understand your vacuum system, work with your vendor if you're buying it, understand what you're getting, or figure it out yourself. I'm a big fan of eliminating surprises. And we are at a good point in history. We had been doing this in 1950. We would have been making a lot of assumptions and crossing our fingers when we put the system together that it was going to do exactly what we wanted it to do. Today, the guesswork has pretty much been removed. And there are lots of software packages out there that provide very, very highly accurate models of gas flow, conductance, and pressure profiles in vacuum systems. I'll give you the couple examples I give you here is MoldFlow, which was developed by CERN. It was a package that was designed for CERN to be able to build their chamber and know with certainty that it was going to do what they needed to do so they could carry out their experiments. It's incredibly powerful. And there also, of course, COMSOL Multiphysics, which is now a paid code, can also include a vacuum system design module, which will allow you to do things like pumping system sizing and implementation, figure out where to put the gauges so that you're not in the wrong place. It'll allow you to do ultimate pressure calculations because it's material aware, right? You can enter outgassing rates, or it knows the outgassing rates for a lot of materials. You can do pressure distributions. You can do gas conductance calibrations, flow control requirements. You can look even, if you bring in the thermals, you can also do thermal gradients and pressure on pressure distribution. And you can do a lot of gas dynamic calculations like mean free path and so on for free energy, high energy physics experiments and so on. So this will actually allow you to do things like even calculate. I saw a poster this year at AVS on that, where somebody was using one of these packages to figure out how often they needed to regenerate their getter pumps in their system, and they were able to pull it right out of the model. The other thing too that I'm a big fan of is when it comes to vacuum system design is if you're a big installation with a lot of vacuum systems and you have vacuum problems every day, either retain a consultant or hire a full-time vacuum guru to design and maintain your vacuum systems. This is priceless. I see this all the time. I'll walk into a billion-dollar corporation that makes tools for the semiconductor industry, there are thousands of employees in the company, and you're looking for the vacuum guru, and what you find out is that there is one guy out there that is kind of the guy that they go and ask the questions about, and for the rest, they just rely on their experience from the past. It's only recently that I've actually started seeing that, particularly in the semi-industry, that they are developing groups where they're retaining vacuum experts with COMSOL, mold flow experience, where they will design the vacuum systems from the ground up, and they know exactly what they're going to get from the beginning. Very often I've gone to, particularly when I was part of Brooks Automation, where we did a lot of pumping, right, cryo pumps. We would go in, the system had already been designed, and we would look at where the pumps had been placed, and it was the worst possible place to put pumps in that particular multi-million-dollar tool. Of course, by then, a retrofit is not possible, and the only recourse for the tool designer was to put more pumping speed, which is very expensive, and of course could get passed on to their customers, that extra cost. I also a big fan of attend vacuum conferences. Particularly, I'm involved with the Vacuum Technology Division group of the AVS. We do talks on this all the time. We had a lot of talks this year on outgassing properties of stainless steel materials. Lots to learn, lots of people to ask questions to. Of course, join the AVS, join your local AVS chapter, network learning opportunities all over the place. There is one here, right here in the area where I am, which is Colorado. We have the Rocky Mountain chapter of the AVS. We get together once a month, and we exchange horror stories, what's going on in your vacuum systems. We exchange tips on the latest equipment that we bought, how to maintain our systems, and so on. Sometimes we are competitors, so we can't tell everybody what we're doing, but we can always share stories, and we can always make ourselves better and come up with continuous improvements in our processes. Big fan too, get to know your local vacuum equipment reps. I can certainly tell you our local rep here, he's the guy has a PhD in chemistry. He shows up to support your vacuum equipment needs, and you have an expert right at your door. So know your vacuum equipment reps in the area. A lot of them are really, really good and helpful as well. Subscribe to Vacuum Tech forums on LinkedIn, big deal of that too, big fan of that. And what I would tell you is shamelessly contact experts for advice. You can find them online. You can find them via AVS, right, through short courses and so on. Don't be afraid to ask. We all love to talk vacuum, and we are here to help. Okay, so we talked about the vacuum pump down process. System gets pumped, samples get loaded, right here. The system gets pumped down. We achieve base pressure. Now, what's going to happen typically is we're ready to start the process. Gas is added to the system, and it is we went to this low base pressure here to assure that when we add this gas here, the contribution of the gases that were left here at base pressure is not going to affect the yield of our experiments. Then typically some process starts. In this case, it's a vacuum deposition. A plasma strikes, some argon starts bombarding a metal target, and then a substrate start to get coated. When the deposition ends, right, we go ahead and we pump the system down again, we open the door, and this whole process starts over. Again, base pressure, different from the ultimate pressure, right? And all we are trying to do is control the initial conditions of the vacuum system before we start the deposition, or in this case, the process, which is a deposition process in this case, in this chamber. During process, obviously, the same rules apply. Nothing changes here. The only difference here is that the pressure in the chamber during your process is now Q over S. S is the pumping speed of your pumping system. You might have a choke here sometimes, right? And Q is whatever gas you're letting in, usually through some combination of valves and mass flow controllers in those systems. And of course, knowing S in your system is very, very important. That goes back to the know your vacuum system. I cannot tell you how many times I will go to a customer to try to troubleshoot a problem, and my first question to you will always be, what's your pumping speed? And I would say, 60% of the time, the answer is, oh, I don't know, and then that makes the diagnostics a little more complicated, in this. And particularly if you're trying to figure out process pressures, your flow into your system is going to be related to your pumping speed. So if you need to order a mass flow controller, you're going to need to know what your pumping speed is. So as far as process goes, gas pressure and chemical composition are critical, right? So during your process, you're going to control not only pressure, but also chemical composition, which is why it is important to achieve a well-known, a well-defined base pressure. This careful gas composition and control is required to produce parts with the required chemical stoichiometries. Use high quality, which means that not only do we have to be careful that we achieve the base pressure, but also we want to be careful that when we deliver the gas, we use high quality gas flow controllers. We use high purity gases, right? We got to make sure that the gases that we use have the purity that is required for our processes. And what is really, really critical, accurate gas pressure control is required to assure proper pumping operation and plasma processing conditions. So it's not only important to know what your pressure is to keep the process stoichiometries, right, all the coating stoichiometries and so on well known, but also to make sure that your pumps are operating as they're supposed, to make sure that your plasma conditions are as they're supposed. Very often plasmas have very, very tight requirements. So you also have to remember that power always gets dissipated during processes, so inside the vacuum chamber, and that increases outgassing levels during the process. So you need to understand that as well. So, when I'm going to go through these very quickly, the thing that it becomes very clear as you get to this point is that a modern vacuum system, right, is more than just a chamber and a pump. There are a lot of different components that go into that chamber. So complete implementation of a vacuum system for manufacturing requires a broad range of vacuum technologies and components. And you need to, the more you know about them, the more you understand them, the better it is. And we have just spent a lot of time talking about outgassing, right, and designing your vacuum system in a rigorous manner to get to base pressure. Okay. Two very important concepts as well. Here are the concept of vacuum system standardization. This is particularly important for facilities with multiple process chambers. And I cannot be, I cannot emphasize this enough. Vacuum facilities with multiple process chambers should drive towards standardization and continuous improvement. If you standardize your vacuum system, so in other words, you make all your systems as close to each other as possible, then you now have huge advantages. You have the opportunity to do chamber matching, which I'll talk about in a minute. You have economic advantages in the sense that you can now order systems and components in quantities, and you get a OEM discount on that. Your amount of training that is required for operators going from one system to the other goes down. Your spare parts inventory goes down. You're always ready in case something needs to be diagnosed and fixed very quickly. It's easy to have a large inventory of parts, and you can use them on multiple various systems. And also, you have, for continuous improvements, which I hope all of you do, you have a shared continuous improvement opportunity. If something works in one of your chambers, and all your chambers pretty much operate the same way, now you have an opportunity to use that in the rest of your vacuum systems. And then, by vacuum system standardization, I wanted to bring to you a very important concept, the one that I'm using now here at work for both R&D and production, which is the concept of a vacuum system as an instrument. And we're going to talk about this next. Okay, vacuum system as an instrument. What I mean by vacuum system as an instrument is we all have processes we have to do, and they have to be done inside these chambers, which are part of a vacuum system, and they all need to do things like, pump, measure pressure, deliver gases, apply RF, and so on. I consider all those things to be building blocks that can be grouped together into a unit. And that unit, then, I like to think of it as an instrument. So basic vacuum system operations are regulate pressure, vent to atmosphere, bake out, operate load lock. So if you look at this graph right here, this block of parts right here, this is my vacuum system, right? And to that vacuum system, then, I connect, typically, a computer which controls the process steps. I will connect maybe devices under test. Like in my case, I will connect a bunch of gauges that we need to calibrate and verify before we send to the instruments. And I will have a bunch of test and measurement equipment. What we are doing currently at our factory is we're putting a dividing line right here in our chambers. So everything that happens on this side of the chamber becomes a black box. And all the process control steps, all the DUTs that get mounted, all the test and measurement equipment that gets connected to this black box as if it were an instrument. And I'm going to show you on the next slide what I mean. This is a typical vacuum system as an instrument for us. So the black box right here is our instrument. This is the vacuum system. Everything is there. On that system, in our case, we load gauges that then get shipped to our customers. On this right side here is all the process control, which includes recipes or scripts, all the test and measurement equipment that is required, and so on. So what's the advantage of doing this? Well, basically, all of these, you can think of it as an instrument with a little port on it. And then the test equipment, the process control, and so on, talks to this vacuum system via that port, and it couldn't care less what pumps we have, what mass flow controllers we have, and so on. All this system has to do right now is say, hey, I need your vacuum system to go to this pressure, and I need you to stay there for this amount of time, and I need you to fire up the plasma, for example. So by doing that, it doesn't matter what the exact makeup of this system is. This process control rack here with its process can be then transferred to any chamber, any vacuum system in my factory, and it will be able to execute that exact same process without knowing exactly what is under the hood in the system. Okay? So in other words, this thing here, this left side, all this block of pumps and valves and chambers and so on, it becomes this virtual instrument, which I can talk to through a port. I just put my samples in it, I close the door, I bring my process module to it, and I'm off to the races. What does this do? Right? It gives me this opportunity to then have, in our lab we have, if you look at these vacuum systems, I have 5 of these sitting in different locations. There's one right behind those shelves. There are 3 more behind this door. All of them have different components on them. Different pumps, different, but they all respond to the exact same commands. So if I say, I need your vacuum system to go to this pressure, I can send the command to them to its onboard computer, and it will go there. And so I can now use different process control racks, which do different things in my lab, to control them. This gives me a lot of flexibility, right? And everything, of course, in this case is modular and it's on wheels. So I can grab this rack right here, move it on to a vacuum system that is in that room, and I can start this process that I was doing here in a chamber that maybe is mounted inside an environmental chamber. And as far as this system is concerned, it couldn't care less what the system looks like. It just provides instructions. So very, very important concept, the concept of vacuum system as an instrument. And of course, the other important concept is that of chamber matching, which is a concept that is critical, particularly in the semiconductor industry. In chamber matching is all about optimizing the operating. It's all about optimizing operating parameters in one golden tool or chamber, and then duplicating them exactly across all other tools in your fleet to obtain perfectly matched performance across the production floor and even multiple locations. This is easier said than done, but it's not good practice to have your processes being linked to being different in every chamber. If you're making the same parts in 3 different chambers and you're finding that you have to do completely different things to arrive at the same result, here the opportunity for continuous improvement is to think about chamber matching. Chamber matching has some critical requirements. You need standardized vacuum chamber design. You need accurate and repeatable gauging. You need well-documented processes. You need good vacuum practices. And it relies heavily on statistical process control. And I have a link here through Applied Materials that you can go to and start reading about how chamber matching is used across the semiconductor industry. And it shouldn't just be a semiconductor industry thing. We use it in our facility. We are not making semiconductor chips, but we have embraced some of these same concepts in our lab. Okay, so this brings us to pressure gauging. And what I'm going to do is we have a couple minutes left. I'm going to just set it up, and then we're going to get into chamber gauging and into pressure gauging in the next section. And we're going to combine pressure gauging with RGAs as well. It'll all work just as well. But as a preamble to this subject, what I wanted to tell you is, and I'm not going to go through all the different kinds of gauges and so on. I'm just going to touch on just the basics, and I'm going to give you the rest of the slides for you to go through. But what I'm going to tell you is, and I know I said this before, is accurate pressure measurement is essential for an efficient and repeatable process. You underestimate the pressure readings with your gauge, right? You're going to start at a higher pressure than you think you are. You're going to have reduced yields. I can guarantee you that. If you overestimate the pressure with your gauge, what's going to happen? You're going to be waiting longer than you should to achieve base pressure in your systems. You're going to be throwing money out the window here, leaving it on the table every day. So as we start talking about gauging, we're going to need to talk about technologies. We're going to touch on direct versus indirect pressure measurement. You're going to have to account the pressure ranges that you're operating on. You're going to have to account the accuracy and reproducibility requirements for your system. You're going to have to consider repeatability, which is the ability of the gauge to read the same values, time after time with good, repeatable, precise readings with no variability. Connectivity, right? What kind of flanges you have, what kind of flanges you have in your system, how you're going to mount them on the system, where you're going to put them in your system. Location, right? What's the best place to put them so that they properly represent the pressure of your process? And then physical factors around. Do I have magnetic shields around? Am I close to heat sources? Is there an RF noise around? Are they going to be affected by line of sight to the position source and so on? And of course, you're also going to have to consider things like chemical factors. Are there corrosive gases present? Are the gauges going to get contaminated or coated in any way? And so on. So with this, we're going to then move on to gas pressure measurement. And I'm going to talk a little bit about how to select the right gauge for your process, and then we're going to move on in the next section to residual gas analysis, particularly for pump down monitoring with RGAs, and we'll spend some time talking about gas analysis during pump downs, which is now going to start making it a lot easier to understand the kind of things that I was talking about when I was talking about gas and water as a buffer during your base pressure. So anyways, I went over a little bit, but sorry about that. We'll be back in about, we'll be back, what is it now? For me, it's 12:51. I'll be back at 1. And if there are any questions, I'll spend some time doing that. Thank you. Hello, we're back. All right, I saw the recording started again. I hope everybody can hear me okay. I have a couple questions. These are good questions. It's funny, one of them, I just went through this about a week ago. So it's a question, I hope I say the name Ivan Spector. In many deposition chambers, I have seen aluminum foil coating components to protect components. Then when you want to clean the chamber, you simply change the foil. However, this creates large outgassing surface areas. It's also not very reproducible. I was just at a site a few weeks ago where they do exactly the same thing. And the fact is they were installing a residual gas analyzer into the chambers just to try to understand the difference in outgassing between having the aluminum foil in that chamber versus not having it. As is generally the case, right, this was a coating, optical coating deposition chamber, big chamber, has two ports, one in the front, one in the back, you can get through. And they put the aluminum foil, you know, just almost everywhere to avoid the buildup of the dielectric coating material, right, over time in the chamber. It's not just that the material as it accumulates, right, it's coating the walls, but also what ends up happening over time is it also changes the dielectric properties of the walls, right? It makes them non-conductive, and that can create fields inside, you know, charged particles and so on, accumulate on the walls, can affect the fields, and then it can affect the uniformity of the coatings in the chamber. So using aluminum foil was their solution. The thing to keep in mind here is if you think of it this way, right, if you have your cylinder, you know, this chamber was kind of cylindrical, kind of like a flat walls, but you know, the round doors as typically the case. And then they would just basically line the entire thing with aluminum foil on the outside. So what does this mean now? It means a variety of problems. The first one is the aluminum foil that you're putting in, I promise you, even though you might be using the vacuum quality aluminum foil, I promise you it's not as carefully handled as, you know, the stainless steel that was used for your chambers. So every time you're kind of getting a fresh dose of aluminum foil with contaminants in it, which most likely is going to be all hydrocarbons. By adding the aluminum foil, funny enough, you triple the surface area of your chamber, because you have the wall, the chamber walls, then you have the outside surface of the aluminum foil, and then you have the inside surface of the aluminum foil. And if you're coating the entire surface, you basically just tripled the surface area of your system. And as I said before, right, the Q outgas per square centimeter, before you had to worry about the outgassing of this surface of the vacuum chamber, now you have to worry about the outgassing from 3 times that area, which means the outgassing is 3 times higher. And that means that you're going to have to pump down for a longer amount of time. So yes, the bottom line is you're telling me, well, this is not very reproducible, right, when you use aluminum foil. I fully expect that. Every time you put the aluminum foil in, you're not going to get the same amount of surface area, right, because you know how it is. It folds, you start wrapping around certain structures, so it clings to whatever it is that you need to clean. You have trapped volume in there. You know, your guy has to be working with gloves, touching other things, so it's bringing contamination with the aluminum foil. The aluminum you use is, you know, might come from different sources. You might get different batches, will have different amount of contamination, and you have the larger volume. So your question is, what is the best practice in this case? Well, for this customer, right, there's so much stuff flying around the chamber that they do want to protect some of the critical components, you know, like their gauging, their motor shafts, and you know, the stuff that they use for the orbital, right, spinner that they use on their chamber. All of that, they want to protect it from line of sight contamination. So in their particular case, what they're trying to do now is they're looking at doing pump downs back to back with a residual gas analyzer and looking at the components that are outgassing, right, as they use or not use aluminum foil, and understanding how the presence of the aluminum foil affects. They're also trying to understand if there's a possibility in their case that the best possible solution is that they can use the aluminum foil. You know, the first time it's going to take a while, but the second time while it gets coated, now with that coating on it, it might actually be okay. And, you know, they might be able to use it 2 or 3 times and then remove it. And during those 2 or 3 times, all the contaminants and all that get trapped on the aluminum foil by that layer of material. So my answer to you would be, if you have to shield things from line of sight, you have to. My choice will always be to use well-defined, metal plates, right, that you can put in strategic places to block line of sight contamination. Like, for example, you don't want your shafts, your mechanical parts that are supposed to come in and out to get coated, so you keep the tolerances and so on. Then I would try to see if there is a way to do that just permanent without aluminum foil. If you have to, use the minimum amount of aluminum foil and do a study and understand what it is that the aluminum foil is doing in terms of outgassing, how much it's costing you. And if you have to also, you can then start playing tricks, like you might have to turn the lamps on, proactively, right, earlier to eliminate the contamination from the aluminum foil and so on. I had another question here too, which is a short one. It's again from Mark Lee. In case we contaminate the walls with less volatile materials, for example, silicon dioxide or metal particles, is outgassing still a serious of a problem in low high vacuum systems? Yes, it still is, right? So particularly if you are opening up the system every time. So you might actually find out that, for example, if you're the outgassing properties of aluminum are pretty good. Aluminum has a very low outgassing rate. So if you started with a stainless steel chamber and suddenly you are starting to spatter aluminum on the walls, which, every time you expose to ambient is going to turn into aluminum oxide, then what you're going to find is actually your outgassing rates might actually go down over time. And then your pump down times actually might get better. On the other hand, it might be the other way around. If the thing that is coating the walls has high affinity for water, you might end up with bigger problems than you had before. Silicon dioxide is a very common coating for the inside of chambers, right? A lot of people treat like Silco steel, right, or treatments like that, where you basically glass coating the inside surface of the system is very common to provide resistance against certain chemicals and so on. But also, silicon dioxide has a high affinity for water. It's a polar, right? It has oxygen, it can hydrogen bond water. So you might find that over time, that in the particular case of silicon dioxide, that water tends to linger a longer amount of time, and the ultimate pressure of your system, the ultimate base pressure of your system might actually go up over time. But guess what? Here's the good news. There are tables for all of these. So if you think that your chamber eventually is going to get coated with silicon dioxide, right, and you know these, then what I would tell you is, okay, since I am going to coat the walls, when I do the calculations of what kind of pumping speed I'm going to need in my system to achieve my ultimate pumping speed that I want, then don't use the numbers for the chamber, the stainless steel in the chamber. Use the numbers for whatever is going to coat the chamber if they are larger, the outgassing rates larger than what the chamber is going to start with. So there's always ways to do these. Nowadays, there is really no, you can't possibly go to your boss and say, if you're designing a chamber and say, oh, I didn't know how to do these, or I couldn't do these. If you know what your process is, you know what's going to be on the walls, you know the size of your chamber and so on, you should be able to size your system properly to achieve your ultimate pressure, even if over time it's going to get coated. I hope that makes sense. All right, so let's move on. I want to get to the fun part now, where everything is, I'm thinking, is all going to start to kind of make sense in terms of the chemical composition of the gases. So we talked about pressure gauging, and I'm only going to spend a few minutes on these. The key about pressure gauging is having the right gauge for your application and having particularly paying attention to the accuracy and repeatability of those gauges. You have to know the pressure in your chamber as good as you can. So I'm going to skip a little bit through here. We went through this slide before. you know, we all know what pressure is. Pressure is caused by the molecules bombarding the walls, right? And then, you know, creating the pressure that we're measuring inside the chamber is actually the force per unit area that the molecules are exerting on the internal walls of that chamber. Of course, this gas pressure is governed by the thermodynamics, and is dependent on the temperature and the molecular density of the gas. It's a funny deal to me that most of us, right, actually the majority of us, we all measure pressure in our chambers, when in reality what we are after is the molecular density of the gas that is in the chamber. When we're trying to code something, where we're trying to do chemistry inside the chamber, what we really care is how many molecules per square centimeter we have, and that's the number we really should have. But what we measure is pressure. And through the ideal gas law, the pressure is related not only to the molecular density, but also to the temperature of the gas. So it's not only important when you measure pressure to know that you have an accurate gauge, you also have to understand that that pressure that you're measuring will represent different molecular densities inside that chamber if the temperature inside that chamber changes. So keep that in mind as well. So I'm going to skip a few slides along the way here. Most of what I'm going to be talking about, as you notice, I'm a big fan of the torr units, or millimeters of mercury. There are some other units you can use as well. But what I wanted to do to start is kind of introduce you to the nightmare of selecting the right proper gauge for your application when you're out there shopping for vacuum gauges. And what I'm using here is I pulled this right out of our MKS website. And this is what it would look like today if you wanted to go buy a gauge from MKS. And it's, you know, you look at this table and you can go and always say, okay, what pressure am I at, right? Let's say that you're going to be operating, you want to measure pressures around 10⁻⁵ torr. You have 1, 2, 3, 4, 5, 6, 7 different options you can choose for, 2 different categories of gauges to choose from. Which one should you use? Well, I'm going to try to help you a little bit, break down what this is all about and help you choose what you have. The first most important distinction that you have to make between gauges for your chambers is what kind of gauge technology you're going to use. If you're trying to measure pressure in your chamber, you would like to be able to measure pressure that doesn't care, with a device that doesn't care what the chemical composition of the gas is. The gauges that are capable of doing that, in other words, they can measure the pressure of any gas that you have in that chamber, independent of what the chemical composition of that gas is, are called direct pressure measurement gauges. And those gauges are typically capacitance-based diaphragm gauges, strain-based diaphragm gauges, and piezoresistive gauges. You might have heard the names like baratrons, right? Common trade name, right, for capacitance diaphragm gauges. These are gauges that are commonly used during process. They can be used all the way down to, you know, if you look at here, you'll find a claim that it can be used to about 10⁻⁵ torr. Typically, I would say 10⁻⁴ torr is the last place where you can reliably control a process with them. But the advantage they bring to the party is whether you have hydrogen on the system or argon or nitrogen, they don't care what the chemical composition of the gas is. They're measuring the force per unit area of that the molecules are exerting on a membrane, and they are independent of chemical species. There is also another group of gauges, and these are particularly used for lower pressures. You know, as the pressure starts to drop below 10⁻⁴ torr, right? They become even more important, which are indirect gauges. And the indirect gauges are the ones that don't directly measure pressure, but rather measure some property of the gas that is related to pressure. And they are internally able, by measuring that property, which could be, for example, an ionization rate or a thermal conductivity of the of the gas. By doing that, they can tell you, they can calculate what the pressure of the gas is. The good news about those gauges is that they can measure very low pressures. The bad news about these gauges is that they need to, they are calibrated for specific gases, typically for nitrogen gas. And so the pressure calculation that they make is based on assuming that the gas that is inside the chamber is the gas for which they were calibrated. And some of them will have, they'll give you the ability to switch between different gases, but it is very important not only to get accurate numbers, but also for your own safety sometimes, that you understand that when you're using an indirect pressure measurement gauge, you are not measuring pressure directly, you're measuring a property of the gas that is related to pressure. And there is an assumption being made as to what the chemical composition of that gas is when the pressure calculation is done inside that gauge. So let me give you the 2-minute or the nickel tour of how these two technologies work, because I want to really get to, we're on block 3 right now, I really want to get to residual gas analysis. Okay, so let's see if I can do this. How does direct pressure measurement gauge? And a typical direct pressure measurement gauge is based on this principle. Imagine that you have two chambers here. You can see the light green and the dark green chambers, and you have a membrane in the middle. And at the beginning, the two pressures P1 and P2 are the same. This membrane is now under no force, no deflection force, and it's just sitting there. If I introduce some more gas onto the right side, I increase the pressure P2, what's going to happen? That membrane is going to deflect, right? And then the amount of deflection, D, that is going to happen in this membrane, right after it deflects, D is going to be proportional to the difference in pressure between those two gases, right? The gas on the right side versus the gas on the left side chamber. This is basically how direct pressure measurement gauges work. What they will do is they'll have a membrane inside, and they will measure pressure differentials. And you can operate them in the absolute or in the differential mode. In the absolute mode, when you buy a typical baratron gauge, what happens is you have the left chamber be a vacuum chamber, right? It's a little evacuated area, and there is a membrane there. And when gas comes in, it starts pushing on that membrane, right? And the deflection now is proportional, since P1 is 0 now, the deflection of this diaphragm now is proportional to the pressure P2 on this chamber. In a differential gauge, of course, when we go back to the example that we had before, and now the amount of deflection is proportional to the difference in pressure. In a capacitance manometer, that deflection, like the typical baratron products that many of you probably use, what you find is that the way the deflection is measured is by measuring the capacitance between that diaphragm and some other counter electrode that is there. And that is why it's called a capacitance diaphragm gauge. As the diaphragm moves, right, and it doesn't care what kind of gas it is, it's completely gas independent. As the diaphragm moves, because the pressure increases, the diaphragm gets closer to a counter electrode, the capacitance goes up, and that number is measured and turned through a stored internal calibration into a pressure reading. There are other devices like piezoresistive diaphragms and so on that do the measurement of deflection by looking at the stress that is induced on the diaphragm while it's being deflected. Regardless of the way this is done, these gauges that measure the deflection of the diaphragm are measuring the force that the gas applies per unit area, and they are direct pressure gauges that don't care what the kind of gas it is. So there's a lot more detail on all these. Here are some examples of capacitance manometers from MKS in this case. And you can buy them with standard accuracies as good as 2%, with high accuracies, 0.05%. You can buy them, standard, high, small packages, hot packages in case, you have substrates that could deposit on those. You got to protect the diaphragm on these gauges, right? And of course, differential gauges as well. The typical application of these gauges is for process pressure monitoring and control, load lock pressure control. They're used a lot like pressure switches to say, okay, the load lock is now at atmospheric pressure, the membrane is not deflected at all, it is time to open the door. They're also used in the presence of corrosive gases because you can buy them with heated. You can also use them in the presence of corrosive gases like fluorine, where special treatments and materials are used on the membrane to protect it from a chemical attack. Capacitance diaphragm gauges are also used a lot for calibration of work gauges in your facility, and very often also used as high precision gas flow meters. My recommendation to you is if you buy a capacitance diaphragm gauge, only use it to control your pressure up to 3 decades below the maximum or the full scale capacitance, the full scale pressure range of the device. Anything lower than that, the accuracy will go down. And this is very well described in the manuals. Piezoresistive gauges are pretty small. They're the same that are used actually in the tires of cars. And you can buy them in very small packages. My recommendation to you is, if you don't need the high accuracy of capacitance manometers, definitely look into piezoresistive gauges as well. This brings us to the next category, which is indirect pressure measurement. What typically happens is, where do you use indirect pressure measurement gauges? You do it when deflection no longer is going to provide you an accurate reading. So the most common application for indirect gauges is for very low pressures. Though, as you all know, Pirani gauges can also be used at higher pressures, though they will never have the accuracy of a direct gauge. Okay? But so, since the physical properties that are measured by these gauges are gas specific, since the physical properties utilized are gas specific, indirect pressure measurement readings are always gas species dependent, and they require gas specific calibration. So, what do the indirect gauges measure? There is typically indirect gauges calculate pressures based on the measurement or physical properties related to the density of molecules in the vacuum chamber. What they'll typically be measuring is some property that's related to the gas density, which through the temperature is then related to the pressure. So the two most common physical properties are thermal conductivity, and this is thermocouple gauges and Pirani gauges, and gas ionization rates, which is what hot cathode ionization gauges and cold cathode ionization gauges are all about. So thermal conductivity gauges, basically all they do is they measure the rate at which the gas molecules that are in the gas remove heat from a heated wire element inside the gauge. If the pressure in the system in the chamber goes up, there will be more gas molecules taking heat away from this wire, and it will take more power to keep that wire at the specified temperature, and therefore the gauge will interpret that as increasing pressure in the system. The most common example of thermal conductivity gauge is the Pirani gauge. Pirani gauges are used all over the place. Out of this building, we have probably shipped by now, since we started, well over 2 million Pirani gauges to customers. So they're very, very widespread, very used everywhere where vacuum is present. I have lots of slides on how the gauges work. Here's the little wire that is responsible for that in this case, in this particular gauge, this wire is kept at a constant temperature, and the power that is required to that is what's measured, and increases with temperature, increases with pressure, I mean, and is used to measure the pressure in the system. There is only one thing that I want to measure about Pirani gauges that is very, very important in terms of, I don't want to leave this subject without doing this, is that the pressure indeed is species dependent. So you have to be very careful. For example, what you have here is a plot that shows the the true pressure in the system versus the indicated pressure by the gauge. And what you can actually see, right, as you expect, for nitrogen, which is where the gauge is calibrated, there is a one-to-one correspondence right here. However, with argon, right, this curve right here, you can see that even as the pressure increases, right, and reaches the atmospheric value here at the top, the argon levels never reach any higher than about 25 torr. What this means is that, and I have seen this happen, I actually had a grad student one time in blow up a vacuum system, is that you can have a vacuum system with argon in it and a Pirani gauge connected to it. You keep increasing the pressure of argon in that chamber, and the Pirani gauge will not reach higher than about 40 torr. And you can keep doing that until the vacuum system will actually blow up on you. So this is not only important because you need to be careful that you measure pressures accurately, but also it's important for your own safety. Okay? So I hope I made my point on this one. When I talk about calibration and applications, Pirani gauges particularly are commonly used for roughing lines, particularly turbo pump 4 lines. They're used in load logs quite a bit. Of course, they're not as accurate as capacitance manometers. Chamber pressure for pump crossover, typically used to cross over to a cryo pump or something like that. And they're used a lot in combination gauges, combination with ionization gauges. These are typical Pirani gauges, small package, larger package. I'm not going to spend a lot of time on these, but they're certainly there, and they're widespread. There are millions of these installed in vacuum systems today. In terms of ionization gauges, there is 2 technologies. Ionization gauges are used to go to high vacuum levels. So this is typically the last gauge that is engaged where in your 10⁻⁵, 10⁻⁶ torrs, right, and under. And there are 2 technologies for them, hot and cold ionization gauges. If you want to know how they work, I got lots of slides on these, on how these gauges work. And I think do a pretty good job at describing how they work. There are different packages, anywhere from small packages to standard packages to high accuracy gauges with high accuracy and reproducibility. There are cold cathode gauges out there. And the only thing that I wanted to mention is I get this asked a lot, is when should you use one and when should you use the other? Hot versus cold. I'm just going to open up these so you guys can read it. Hot cathode ionization gauges, those are the ones that have the hot filament. They use electrons colliding with atoms and molecules to cause ionizations. The source of electrons is a filament, an incandescent filament, very hot filament. Advantages and disadvantages, they are usually more accurate than cold cathode gauges. Not always the case. Be careful with that one. Depends on what product you buy. The problem is that they have a hot filament, and that filament can burn out or it can break out due to mechanical shock. They are more accurate because they have a feedback control on the electron emission current, so you get much better controlled ionization rates on these gauges that allow you to calculate total pressure, you know, with higher accuracy. Cold cathode gauges, on the other hand, they don't have a hot filament, and on the other hand, they are kind of free-running. They are kind of a non-linear free-running thing, and as a result of that, they are typically less accurate and stable. A typical accuracy on a cold cathode gauge is plus minus 30% unless you buy a specifically calibrated gauge. And the lack of accuracy comes from the fact that there is not the feedback loop control on the electron population as there is in hot cathode ion gauges. So in my world, where I have customers choosing all the time, my usual recommendation to customers is if you can get away with a cold cathode gauge, do it. If plus minus 30% for your base pressure measurements is good enough for you, do it. If you need better accuracy, first go to a calibrated cold cathode gauge. If you need even better accuracy or you need a combination gauge, then go to the hot cathode gauge. And I can talk more about this if questions come up. All right, so now we get into the fun part. We have 20 minutes to talk about this. I want to talk about pump down monitoring, and residual gas analyzers. This is my favorite subject, and this is going to be our segue then into how we're going to be proactive about our pump downs and how we are going to avoid delays and make our processes most efficient. So we'll start with kind of a scenario, right, which I'm sure many of you have experienced before. We have a vacuum chamber, we pump it down with all the gas delivery valves closed, but the pressure that's not reached its target-based pressure within the specified amount of time that we're used to. So in other words, we start pumping down, our chamber typically will reach 3 minus 6 torr in 2 hours. It's been 3 hours and I'm not anywhere close to that. And we're all standing in front of the vacuum system, and I dare one of you to tell me you haven't done that before. We're all standing in front of the vacuum system and going, why is it not pumping down? What is wrong with my vacuum system? It worked yesterday, why isn't it working today? I didn't touch anything, I didn't break anything. Why isn't it pumping down? So the questions that immediately start rattling through your head is, do I have a leak? Did I put something in here that is outgassing too much? Did I add a contaminant? Did I forget something inside the chamber? The bottom line is, at this point, unless you have some sort of residual gas analyzer in the chamber, or you're capable of doing a leak detection right at that point, you're pretty much, all you got is a total pressure measurement, which is a single number, which alone cannot help you to quickly and irrefutable tell what the problem is. In order to be able to diagnose, what the problem is, and to troubleshoot what the problem is, what you're going to need to have is partial pressure information, and you're going to need to have chemical analysis available for your vacuum system. And this is where I cannot say enough, partial pressure analysis becomes a must-have. And today, with the reduction in cost of residual gas analyzers in the market, that all got pushed back, and I can take credit for that. They have been lowered down to where their price is comparable to just about anything else you buy to your vacuum system. There is almost no excuse, particularly in a production environment, not to have a residual gas analyzer in every chamber. And we'll see why. The idea is very simple. Complete characterization of a vacuum environment requires not only a total pressure measurement, but also understanding what the chemical composition of that environment is. The instruments that are used for this purpose are called partial pressure analyzers, residual gas analyzers, and more recently, vacuum quality monitors. So what is a residual gas analyzer? I have a picture right here. That's an RGA right there. This is a chamber. That's a 2 3/4 inch cone flat flange for those of you that are hip on flange kinds. And here's a typical RGA, a modular RGA. This RGA is a small, rugged mass spectrometer, which is connected directly to a high vacuum system, and it will allow you to analyze the gas composition inside the chamber. This is kind of how it looks like. You have your vacuum chamber, here's your pumps, right? The valve that allows gas in. The RGA is connected directly to that vacuum chamber. The internal components of the sensor are exposed to the same vacuum environment that is in the chamber, and this is called a direct immersion sampling. Here's an example, right? Here's an RGA connected to a chamber via a cone flat port. This is the small vacuum system. There's a valve, and here's a typical mass spectrum for this device. I don't know if you do RGAs now, if you've seen RGA spectra, but what you typically get out of a residual gas analyzer or a partial pressure analyzer is a spectrum that looks something like this. There's masses on the x-axis, and there is intensity or partial pressure or sometimes current on the y-axis. And these peaks here correspond to specific mass-to-charge ratio of different species that are inside that vacuum system. And the amplitude of them tells us how much of them, what the partial pressure of those components in the system are. Okay? So in this case, for example, as I look at these, I can actually see the system has a peak for hydrogen. Here is water present in the system. Here is mass 28. This is probably carbon monoxide or nitrogen present in the system. And then I have a big peak here at what looks to be 32, which is most likely oxygen present in this chamber at a partial pressure of about 2.5 E-7. This information is critical, right? RGAs, here's another example, right? They're often used to monitor the quality of the vacuum by easily detecting even the most minute traces of impurities in a gas environment. What's incredible is with a high-end quadruple mass spectrometer RGA, you can measure partial pressures down to 10 to the minus 15 torr. So that's a lot of decades of dynamic range, right, for pressure measurement. And here's a perfect example, right, where I have a vacuum system pumped down. Here's your water peak, right? Here's some, looks like this is most likely like some carbon monoxide from the filament. And then here's some oil peaks in the system. And by doing a very quick analysis, you can determine the amount of residual oils in the chamber, and you can decide whether it's okay to start your process or not. The other reason why I think RGAs are so important in your chamber is because not only are they used to, can they be used to analyze the composition of your gas during pump downs, but also because they can be used to do helium leak detection, which I'm sure most of you have done or have seen somebody do, right, in your labs, and you know that is like the accepted methodology to do to pinpoint the location of air leaks in a system. So it allows you to know if there is a leak in the system, an air leak in the system, and also pinpoint the leak in the system. So on the left side here, I have a typical portable helium leak detector that will be connected to a vacuum chamber in case a leak is suspected. On the right side, I show you the leak detections, the same sort of leak detection performed with an RGA. Why am I such a proponent of using RGAs for leak detection in your systems? Is very simple, and it's because with an RGA, you can do leak detection with any gas. You don't just have to do it with helium alone. And also, you can do what's called dynamic leak testing. So here's the deal. Let's just say that you start pumping down your vacuum system, and you cannot reach base pressure, right? It's clear you're not going to get there. You know, we're back to the, you were supposed to hit your 3 minus 6. You're stuck at 1 minus 5, and there is no way I'm going to get there. You suspect that, you know, you don't know what's going on. It could be a leak, or it could be contaminants in the chamber. So what many people will do is they will say, all right, it's time to bring in the helium leak detector. What does that mean? You're going to have to break vacuum. You're going to have to connect the helium leak detector to that vacuum system. You're going to have to pump down via that helium leak detector, and you're going to have to start spraying helium around. So this means you got to go find the helium leak detector, connect it, wait for it until it achieves vacuum equilibrium with the rest of the chamber, and then you're going to start leak checking. Versus the idea that as you're pumping down and you're at 1 minus 5, you can just now turn on the RGA and start doing helium leak detector right there, looking at the helium mass, which is 4 AMU, and doing leak detection right there on the spot. What this does is uses the pumps that are already there in the system, so you don't have to spend a lot of money buying an expensive helium leak detector where part of what you're paying for is the pumps themselves. You also don't have to do this with helium. You can spray dust off if you want and look at 54 AMU and do helium leak detection. You can spray argon if you want and look at mass 40 around the system and not rely on helium tanks, right, that have to be in your system. You can even go and add some acetone, on certain seals and look for acetone coming in. So the immediacy, just being there is a good thing. The other thing too that happens is you get to test under the exact same conditions that your process is happening. So very often what will happen is by the time you connect the helium leak detector in your system, you have changed conditions. You have closed some valves. You have to isolate the turbo pump from the rest of the system. You might actually be hiding where the leak actually is. Whereas if the RGA is present, under the same conditions that your total pressure gauge is seeing, now you have a better chance of finding where the leak is. So, why leak test with an RGA? Use any gas, not just helium. It allows you to do this dynamic testing capability, which is you're testing under the exact same conditions as your total pressure gauge is operating. You can do this inside-out leak testing. I'm not going to go into that right now. You also have, you can configure your RGA software to provide direct leak rate display just as your helium leak detector does. So if you need to know how many total liters per second leak rate you have, the RGA will give you that number too. All software packages allow you to do that. And of course, if you're going to buy the RGA for this leak detection, you can also now use it for diagnosing what the gas, if there is not a leak in the system, you can find out if there are contaminants in the chamber as well. Maybe that's the reason you're not pumping down, and then you can go and resolve the problem by maybe doing a bake out. But you can also then use the RGA during process itself to look at the purity of the gases in your system. So, with the RGA, you can also distinguish between outgassing, virtual leaks, and real leaks. It's going to be much more affordable than a portable helium leak detector. It's going to require lower maintenance and less expensive maintenance than a helium leak detector. And it will allow you to have your own dedicated RGA on your chamber and not have to share your leak detector with other people, which by the time your leak manifests itself, somebody else might be using the shared helium leak detector in your lab, and now you have to wait until that is done. So I cannot say that enough. Having an RGA in your chamber is your key to fast diagnostics and proactive diagnostics during pump downs, and it will pay for itself very, very quickly. Okay, so part of the deal of using an RGA to do helium leak detector requires knowing your pumping speeds, and this slide talks about that. You can always connect a calibrated leak into, helium leak into your chamber, on a T or, on the side of the chamber, and you can use that leak to calibrate the RGA for the direct display of helium leak rates. So let's see, how much time do I have? I don't have a lot of time left, so I'm going to skip all the slides on how the RGA works, and I'm going to move to the fun part, which is how to use an RGA to do vacuum system diagnostics. So there's a lot of slides here. These are all for you. I hope you go through them. Here's a slide on how to, where and how to acquire calibrate leaks, which are great to have on your system. And then what I really want to do now is talk a little bit about vacuum diagnostics. So like I said before, total pressure readings are typically what you use right today to characterize if you're, to decide whether you're at conditions to start your process. Not enough. It's just never, if there's a problem, you're stuck. You're going to need an RGA to do root cause analysis if something goes wrong, if you're not achieving your base pressure. And at that point, then, spectral analysis is going to become an essential skill. So let's talk a little bit about that. The first thing that you have to realize when you turn an RGA is that the RGA by itself will also have some gases, right, that will outgas from itself, right, when you turn it on. So typically, when you turn on an RGA for the first time in a chamber, even if it's a pristinely clean chamber, what the species that you're going to be dealing with are going to be, this is typical, right? It's not every one of you. Sure, you're going to tell me, no, I also see these and that, sure. But on a typical high vacuum system, particular one that just got put together, what you're going to see is hydrogen, water, fluorine, carbon monoxide, carbon dioxide, methane, and hydrocarbons. Okay? So here's some examples of what you're going to see in a vacuum system. And what I'm doing here is kind of trying to close the loop with you. I'm going to show you what typical vacuums look like in chambers at different levels. This is an example where I have an ultra-high vacuum system that I pump down to ultimate pressure. In an ultra-high vacuum system, the vacuum environment is going to be dominated by hydrogen. Hydrogen is at 2 AMU, it's this peak right here. And 95%, if you know that your ultimate pressure in ultra-high vacuum system, if your hydrogen is at 95% or so. Many users, all they'll do is they'll just take a look at the spectrum, they'll look at the hydrogen peak, and they can know right off the top of their heads, we don't even have to look at the numbers, that they're ultra-high vacuum. And these are the species that you're looking at here. Hydrogen, water, right, at 18 AMU, carbon monoxide in this case, a lot of this is coming from the filament of the gauge itself, and some oils left in the system. Notice that all of these components, it's not just water, right? In here, all of these components contribute to the total pressure measurement in the system, right? But in the case of a UHV system, it's all dominated by hydrogen. What happens if I go to a high vacuum system? Well, the spectrum looks completely different. In a high vacuum system, the spectrum looks like this. And what you can see here, this is a chamber, this is a stainless steel chamber that I pumped down to ultimate pressure. And I gave these a couple days, and I said, let's see where we get. In my case, in my chamber, the best that I typically do is about 5E-8 torr, is a turbo pump system, unbaked, and this is where I get stuck. And you can see what actually I get here. In a chamber like this, right, the main component is always going to be water. So I promise you, if your vacuum systems, you're pumping down routinely to high vacuum levels, say 10⁻⁴, down to, 10 to the -8 torr, your gas that is left in that chamber when you do that, day to day is going to be dominated by water. How much water? Depends on your pumping system. In a turbo pump system, it'll be somewhere between 75 to 95% water. In a cryopump system, it'll be between 50 and 75%. But water will dominate the spectrum. The rest will be contaminants. It could be air leaks in the system, it could be oils in the system, and so on. But water will typically dominate the spectrum. That's why I always talk about following the water. Okay? One of my recommendations with an RGA is that you always follow the the pump down with it, and that, I show you before the spectrum, right, with in a linear scale where you can actually see the peaks. This is all great, but if you really want to know what's going on, go into a log scale. Okay? In the log scale now, here's my water peak again. Oh, sorry. Here's the water peak again, right? But now you can see over many decades of dynamic range what all the other species in the system are. And it is this kind of information, right, that ultimately is going to be able to tell you if the system is not pumping down. Why is it not pumping down? Is it because I still have too much water in the system and I have to bake out? Do I have air coming in? And I'm going to show you what that looks like. Or is it oils? So, speaking of air. Oh, my mouse is getting a little too tricky here. Actually, here's an example in terms of following the water. This is a spectrum. What I'm telling you, typically at base pressure, you will be dominated by water. Here's a typical analysis for my chamber, right, at about 1E-6 torr. This is another chamber that I have. It's a small turbo pump system, 40 liters per second. Pressure, partial pressure, 7.7 E-7 torr. 77% of this is water, right? And this is exactly what I would expect. So in a typical water range in a turbo pump system, 75 to 90%. In a cryopump system, 50 to 75%. Okay? And you can always, I thought I had another slide here. Hold on. Yeah, here we go. So as far as the differentiating between, when the system is not pumping down, how does an RGA help you identify if you have a leak? The beautiful is that the beautiful part is most of the time you don't even have to leak check. When you have a leak in your system, all you have to do is look at the nitrogen and the oxygen signal on the spectrum. Here you can see it. This is the nitrogen peak, right? That's the oxygen peak. In air, nitrogen and oxygen are in a 1:4 ratio. So if you're pumping down, you get stuck. And suddenly you go look at the spectrum and you go, look, my water is where I would expect to be from my base pressure, you know, already hit the 80-7 torr, but your water, your air peaks are too high, then you obviously have an air leak. And at this point, what you would do is you would take your helium wand, or you could use dust off, and you will look at your helium leak check with your RGA in the same chamber. So this would make your life very, very easy. It would make it very easy to identify leaks. So how do you know if it's air? You look at the composition, right? You look at the composition of the 32 and 28 peaks. You expect a, I actually wrote this backwards, the 28 to 32 ratio in a 4:1 ratio. You can also look as you're pumping down at the trends. If your system is stuck with an air leak, what you'll typically see in a trend is that your water levels continue to drop while your air levels are stuck. And this is why if you have an air leak, pump downs take longer, because you gotta wait until the water pumps down even further to achieve your base pressure, okay? So I have a few more spectra here that you get to save. We are pretty much at our break time here. The last thing I wanted to mention to you is I wanted to bring you back to your attention to spectral libraries, particularly the NIST library, where if you're looking at RGA spectra and you don't know what those species are, you can always go to this website, type the masses that you're seeing, or type the names of different compounds, and it will show you spectra that you can then compare to the ones in your RGA. Also, most RGAs have their own libraries, okay? And most of them also provide some tables with the different compounds and what the peaks in the spectrum are. So, bottom line, good gauging, RGAs in your chamber, use the RGAs to diagnose your pump downs, use them early on, don't wait until you didn't pump down, start checking right away, look for air leaks, look for contaminants early on, be proactive, and if you think that there is an air leak or if the RGA is telling you, use the same RGA to pinpoint. All right, so we'll leave it at this point. On the next section, we're going to talk a little bit about another pressure measurement, partial pressure measurement technique, and we will also then talk about proactive monitoring of pump downs. Thank you. All right, we are back. I can see recording started again, so we're ready to go. I hope everybody's back. Sorry, I ran a little over on the last section. Hope you made it to whatever you needed to do, but we're on the last stretch. I wanted to kind of make a comment on one of these items, because it's going to come in handy on the next section. And I don't know how many of you today use RGAs on your vacuum systems, and like I said before, I cannot recommend them strong enough. I think every chamber should have one today, particularly a production chamber. But you know, as I was looking at this over the break, I'm going to come back to this later on, but I can pretty much just right now show you a little bit of what we were talking about in the previous slide about being proactive in your pump down diagnostics, and also using water as your buffer. What is typically, I like this spectrum a lot. In fact, I'm going to kind of go backwards here a little bit. Let's just say that you have your station, right? And by the way, I do have a question. I'll get to it, but this is fresh in my mind. Let's just say that you just open up your vacuum system, you loaded your samples, right, and you started a pump down. How would the RGA come into play? I would like to kind of go through that whole story. How would you use the RGA to very quickly, proactively tell you that things are going to be okay? Well, for the average person without an RGA, what they would do is they would close the doors, start the pump down, and they would start tracking the total pressure. A well instrumented process would include some logging of the total pressure as a function of time, and hopefully the pressures will be tracking whatever was happening yesterday, and the system will achieve its base pressure when it's supposed to, and everything is great, until it's not. So how would that story look different if you were using an RGA? If your vacuum system is actually not in a good place and is not going to achieve that base pressure, very quickly the RGA could tell you. And this is what I do every time. I don't ever do a pump down without having my RGA turned on at some point or another. So this is how it would work. You would start pumping down, and you most likely would have something like a Pirani gauge or a ionization gauge that would be looking at, or a combination gauge maybe, that would be looking at the pressure in the chamber. And as soon as the pressure drops below the safe pressure value for the RGA, which is typically 10 to the minus 4 torr and under, the RGA would turn on, and you would start collecting data from that RGA. As soon as the RGA turns on, what you would normally see is that the system, at that point, because you just open it up and you're pumping it down, it would mostly be dominated by water. And what you would do is then at that point start looking at the water levels, and you could at that point compare what the water levels on the RGA are to your total pressure readings. Since 95% of that gas is going to be water, you would expect a pretty close agreement between the total pressure readings from your gauge and the partial pressure reading for water in this system, right? This peak right here, the 18 AMU. Now, as the water levels start to drop, right, as the total pressure starts to drop, what you're going to see is the water levels are going to start to drop, whereas the contaminants might or might not drop. Right? This is what I was talking, as the water is dropping, what's happening is you're losing your loosely bound molecules, right? Usually water molecules, loosely bound molecules, water molecules far away from the walls, right? And the water levels are going to start to go down. As that happens, these peaks relative to the water are going to come up, and you're going to be able to see them. So as you're going down, that is the time when you need to start looking at the 28 and the 32 peaks in the spectrum. If the 28 and 32 peaks, which correspond to that could correspond to an air leak, are in the 4-to-1 ratio and are at a value that is higher than the pressure that you're wanting to achieve during your pump down, it is time to stop right there. There is no reason to go on pumping, right, and hoping that you're going to get to your base pressure. You already know right there that you're not going to get to the end. So at that point, you say it is time to start helium leak checking, and that's where you switch over. The other scenario is that as the pump down starts and the water levels start to go down, and we'll talk about that later again by the follow the water, is that you start seeing that these contaminants are already at a pressure higher than your base pressure. If these contaminants are already at a pressure higher than your base pressure, very likely you will not achieve base pressures because these guys outgas very slowly and their pressure drops very slowly. So it is time to go and decide whether maybe what you're going to need to do is a bake out in the system. So what this means is that even if you're pumping down to 10 to the minus 6 torr, by the time you get to 10 to the minus 4 torr, when you can turn the RGA, you can turn it on right there. And you can start looking at the air peaks, and you can start looking at the contaminant peaks, and making decisions right there whether those levels of air and air peaks and contaminant peaks are above or below your target base pressure. If they're above your target base pressure, you're in big trouble. Because you're not going to get there. And it is time right there proactively to do diagnostics. So this is the power of the RGA as far as I'm concerned, and we use it all the time. So to give you an example of what we do here at our Longmont facility is we calibrate. I showed you the vacuum system before. We calibrate and verify every gauge that we ship before we ship it. So they anywhere from 30 to 50 gauges get mounted on a chamber, and then that chamber now has to pump down. And it takes time for that pump down to go down. And of course, we are a business, and for us, time is money. So one of the things that we want to make sure is that we don't have to wait 2 hours before we get to the point where we go, hey, it never got to the pressure, the target base pressure that we selected. So what we'll typically do is we'll load the gauges, we'll start the pump down right away, and in order to know if there is a leak or not, what we'll do is right away, as the pressure achieves the 10⁻⁴ torr, we will turn on an RGA that is mounted on every chamber that we have, and we'll do what I call a proactive helium leak check on that system. What we're checking for is, since we loaded anywhere from 30 to 50 gauges on a vacuum system, there is potential that one of those seals might not be good, and that it might hold up our pump down and our calibration that is supposed to follow. With the RGA, we can very quickly do a helium leak detection, but we also get to see whether any of the product that we put on the chamber is also excessively contaminated. Then what we do is, if no leaks are detected and there is no excessive contamination, is we also turn on the gauges, and we still look with the RGA, and we make sure that nothing is coming out of the gauges as we power up the filaments, because that increases the outgas inside the gauges, and that's how we make sure that you get a clean product as well. So all of that is done in situ. By the time we're all said and done, we know we have no leaks, right? We know that our gauges are clean. We know that our filaments are also clean. And we know that we're going to get to the base pressure in the amount of time that we want it. This takes only a couple minutes to do, right? It's literally a 5-minute procedure, very easy to do. You can even bag the entire system, right, and just spray helium all over it, not try to pinpoint at this point, and you could do this in a couple minutes. So, like I said, I cannot recommend this procedure enough. Have an RGA in every chamber. If there is something that you can do as a best known practice, is add one to your system. And by the way, a lot more of these you can learn through the other short course that we have at the AVS, which is the partial pressure analysis with RGAs, where you will spend 8 hours learning about this stuff. But right now, for these, as part of the best known practices, all I want to make sure is that you don't walk out of here without this bug in your head that says, hey, maybe we should put an RGA in our chambers. Okay. So, all right, so what I wanted to do now in the last section is, by the way, there was one question that I also wanted to address. Okay, yeah, there's actually two questions. Yeah, this is a good one. There is one here that says, okay, here. Do you think vacuum clean stainless foil? And I don't know, I'm wondering whether this is, maybe you can send me a follow-up question. Are you asking whether stainless steel foil would be better than aluminum foil? Or are you asking me if vacuum clean stainless steel foil is good in general? Why don't you send me a follow-up? This is from Joyce Castor. And in the meantime, while you do that, the question here is, I am not sure if you will address this later, but how can you ensure that your vacuum gauge is reading correct over time? This is a great question, and I think we should talk about this. I spent a lot of time talking about, right, the importance of having accurate pressure measurement in your vacuum system. If you don't know what your pressure is, you're going to waste time, you're going to waste yield, you're going to waste samples, you're going to waste substrates. It's going to be a disaster. But then there is the problem, right, that as time goes by, as we all know, gauges drift, so, or can drift. So what do we do about that? Well, there are many different tricks that can be used for this. The first one is, depending on your technology, right? If in your vacuum system you are using capacitance manometers, direct pressure measurement capacitance manometers, this is kind of an easy one because capacitance manometers typically don't drift on their full-scale range reading. The only thing that needs to be done is do a periodic zero on them. As long as you do a periodic zero, they will be good. If you're still not sure, or if you want to do due to ISO certification, you need to every now and then check your gauges. My recommendation is always, there are these special valves you can buy. They're like, three-way valves that you can buy. I know MKS sells it, there are other companies that sell them too, where you can always bring a calibration capacitance manometer, connect it basically to the same port as your manometer is connected, and use a high precision capacitance manometer to check the calibration on your work capacitance manometer. So you basically bring a reference standard, connect it through a three-way valve to your regular work gauge, and then you can make sure that both of them are reading the same, and if they're not, you can always adjust the gauge on the gain on the capacitance manometers until they do. So fairly straightforward with capacitance manometers. And for example, if you go to the MKS website, you'll find lots of application notes on using, I think it's the 609 or 690 product line of capacitance manometers. With indirect pressure measurement, it gets a little trickier, but you can still do the same thing. For example, for Pirani gauges, my recommendation is always, if you're using the Pirani gauge over its entire pressure range, you can always have a capacitance manometer sitting on the side that you can use to check your Pirani gauge. So, for example, if you're using your Pirani gauge in the -2 torr, you can always have a, all the way to the -2 torr, you can use capacitance manometers, a 1 torr, a 10 torr capacitance manometer, and regularly check your gauge. Another trick that works very well, though, for checking capacitance manometers, you can do this with Piranis as well, is to use a flow meter. So remember, P is equal Q over S. With a flow meter, you can dial a Q value for your chamber. So in a lot of particularly semiconductor processes, the way they check that their gauges are working okay at the beginning is they will turn on their pumps. They know what their pumping speed is every day. It's very rare that pumping speed in a system is going to change over time. Pumps either break or not. So what they'll do is they'll start their pumps full speed, and then they'll turn on a mass flow controller to a known value of Q, right, to a flow, and then they'll go measure the pressure. And they'll do this every day. If for the same flow and the same pumping speed, you get the same pressure, P equal Q over S, then you know your gauge is reading the same value. If you don't get the same value of pressure, then this either means that either your mass flow controller changed or your pressure gauge changed. And in my view of things, or in my experience, I should say, most of the time, if you're seeing drift in this way, it's most likely due to the gauge. So this is kind of a way to check your system in real time. When it comes to ionization gauges, you can do the mass flow controller trick. You can use actually a leak valve for that. The other trick that you can use is a spinning rotor gauge. And I don't have spinning rotor gauges listed in the presentation here, but they're very useful. And a spinning rotor gauge will allow you to measure total pressure down to 10⁻⁷ torr, which is, the useful range for a ionization gauge, and the accurate useful range of a ionization gauge. So if you're in any doubt that one of your gauges is not operating properly, you can either bring a spinning rotor gauge to your system, and you can bring the work gauge to the spinning rotor gauge station, and you can compare its readings to make sure that it's accurate, and adjust the readings if you need to. Let's see, another thought that I have for that, because this is right up my, this is in my wheelhouse right now. The other thing that you can do is particularly for ionization gauges, particularly for cold cathode gauges, you can keep tabs on the use of the gauge. Cold cathode gauges have a pretty consistent drop in life. There is a product that we offer nowadays, for example, that includes a dose, it's called, and a dose is kind of like a gas tank measurement. There are some cold cathode gauges out there that do that give you an indication of when it is time to replace a gauge because it has drifted by more than 30%. And the way they do that is by measuring usage inside the gauge, and there are what we call dose inside the gauge, which is correlates directly with the loss of accuracy on the gauge as well. So here are some ideas I threw around. Spent a little more time than I expected on these, but there you have it. Okay, so I got my response to find all metal flakes. Right, so here's the question, right? Would stainless steel foil be better than aluminum foil? If you use it to protect the chamber from deposition, we find that metal flakes more easily from the stainless steel foil. And the question was whether it's better with respect to outgassing. Actually, it is kind of tricky, right? Because if you look at, you can look up in tables, you can look at the outgassing rates of stainless steel versus aluminum. Aluminum, particularly, if it's been exposed to air, you know, it has a layer of oxide on it, typically shows better outgassing values, meaning lower outgassing values than stainless steel does. You know, it would be my recommendation. I would rather use stainless steel than I would use. I'd rather use aluminum than I would use stainless steel. On the other hand, what I'm worried about in most of these cases is not just that the aluminum itself, but rather how it is prepared. So, you know, these foils are rolled and then they're washed, right? And so it is very possible that because of the way the stainless steel is processed, right, with higher temperatures, it's very possible that if you buy stainless steel foil, it will have less contamination than the aluminum foil, which can be rolled, you know, at lower temperatures, right? And, you know, even though they tell you they wash it, there's still going to be whatever it is that they use, coconut oil or whatever it is that usually is used in the rolling process. So the bottom line is the only way you will really be able to answer this question is if, from first principle, is aluminum is better than stainless steel in terms of the metal itself, but I don't know which one is going to get to you cleaner. Aluminum might actually be dirtier because of the way it was manufactured. You know what the answer to this question is going to be in the end? Get an RGA. Put it in your chamber, put aluminum foil, pump it down, look at the residual gases in the chamber, put stainless steel foil, and look at the residual gases in the chamber. And then the other thing too is once you do it, you can even compare vendors as well now and figure out which one is the one. You only need to do this once, but here's the deal, right? You do it once, and then you figure out which one is the best, and you keep it forever, versus living with the wrong thing forever and having every day, you know, extra pump down times, extra flakes, extra whatever in your chamber. So, long answer to your short question, but you know, I think in the end, everything you ask me, I'm always going to tell you, you got to get an RGA. So anyways, let's move on to the last part. We have 30 minutes left. I wanted to talk to you about another gas analysis technology. I'm not going to spend a lot of time on these, but not everybody knows about this trick, so I wanted to bring it to your attention. And it is another device that you can mount on your chambers for high vacuum applications that can provide gas analysis. And the reason I like to talk about this device is because it brings another dimension to the party, and that is speed of analysis. And particularly for people that are, these days as processes are getting faster and things are switching in and out faster of chambers, and you need devices that can do analysis very quickly, this might be the ticket for you. Things like nowadays ALD, right, where every step is only a few seconds, or hard disk coatings, right, on the platter of a hard disk. That is 3.5 seconds per cycle. And RGA is not going to have the time to track that process and give you full spectral information. Is there something else I can do? Well, the answer is yes, there is another technology that is parallel to RGAs that is called the vacuum quality monitor. I give you here some references to it. And, sorry. And this technology is, again, a mass spectrometer, but it's a different kind of mass spectrometer. If we speak in general, and we didn't go through the fundamentals of mass spectrometry, but all mass spectrometers work the same way. They have an ionizer, a mass separator, and a detector. So the idea is that a small fraction of the gas molecules that are inside the chamber go through this ionizer. They get ionized, so they go from being neutral molecules to being ions. Then they get thrown into a mass separator, separated from each other based on the mass-to-charge ratio, and detected. And this is how the spectrum gets created. So here's a cross-section of what a VQM looks like. Here's the ionizer is on the top, mass separator in the middle, and a detector at the bottom. This kind of gives you the scale, so it's not much bigger than a Newt ionization gauge in a system, so smaller than a typical RGA. And the big difference between the VQM and a quadrupole is that whereas in a quadrupole, the ions get formed and then separated by a filter and detected one at a time, in the VQM, what we have actually is an ion trap. So all gases get ionized at the same time. All of them get stored inside this cylindrical structure, which is an ion trap, right? All of them are present at the same time, and then they're scanned out very, very quickly to generate a spectrum in a matter of milliseconds. So the ionization happens inside this volume. All the ions are stored here simultaneously. They are all ejected mass dependently, but that's done very quickly, so you get very fast scanning. There is a slide here that describes how all this works, the ions, how the ions are stored, in oscillating frequencies. I'm not going to go into the details of all that, but what I wanted you to know is what the advantage of a VQM is relative to a quadrupole. It's not for everybody. It's not going to be the answer to all your problems, but I wanted to show you what you can do with a VQM compared to a quadrupole, because whereas everybody knows what RGAs are today and what they do, whether you have one or not, you've seen them, you've used them, or you've heard about them. Not everybody knows about this technology, and it's incredibly useful. I use it all the time. So here's the deal. So this graph is very telling. What I have in here on this graph, this first top graph in blue, is a spectrum generated by the VQM, right, in 70 milliseconds. So 70 milliseconds, you get a full spectrum. And you can see, all the usual gases, the nitrogen, the oxygen, so it's a little bit of an air leak in this system, the carbon dioxide, and so on. And in red, I show you, at the same time, how much data would the fastest quadrupole in the market today collect in the same amount of time that this RGA completed, that this VQM completed the scan. You can see I only got one peak, the hydrogen peak, out of the spectrum. So in 70 milliseconds, I was able to collect a full spectrum with a VQM, whereas with the RGA, with the RGA itself, I was only able to look at one species at a time. At the bottom then, I also do something different. I say, well, let's be fair and let's let the RGA complete the scan, right? So 1.5 seconds later, the RGA is done with a 100 AMU scan, as you can see right here, right? And in the meantime, while that is happening, while that 1.5 second scan completes, in blue I show you the average data from the trap below. And you can see that in the same 1.5 seconds, the RGA collected a bunch of spectra. I think it was something like 7.5 spectra, right? If I can do math. Something like that. And then you can see that some of the peaks that are showing up here, like the perfluorinated compounds, right, at the bottom here, are actually missed in the, right, almost missed in the RGA, in the noise, whereas they are very clear in the case of the ion trap. So what you have here is a very small device, very low dissipated power, that now allows you to either collect spectra very quickly and see very fast transients in your system, or if you wait for it to average spectra, allows you to see things that normally you wouldn't see with the RGA. So the idea here with this technology, which is it's kind of complementary to RGAs, is very fast, right? The commercial product is about 85 millisecond scan for 145 AMU. Wide pressure range, 10⁻⁵ to extreme high vacuum, very low power requirements, very easy mass axis calibration, very low outgassing. So if you're in a situation where the RGA by itself is outgassing too much and you have a hard time telling what's real contamination in your system, what's outgassing from the RGA, this might be your ticket. Of course, reduce outgassing levels because of its small size, and particularly good for ultra high vacuum and extreme high vacuum applications. The other thing too that this system brings to the party, super high resolution at low masses, very fast transients. Here's a system where we were able to do in real time, look at a transient. This is 253 milliseconds per reading, right? Where we saw a transient from 10⁻11 to 10⁻10 torr in pressure, and we have all the gases at the same time. If I had tried to do this with an RGA, I would have hardly been able to collect one mass, 1 point. So incredible technology. I don't want you to go away from here without knowing about this. How would you use this? Exactly the same way you would use the RGA, with the advantage that if you have processes that are really fast, now you can actually track them in real time, and you can look at all the species, right, without having to go and choose, 2 or 3 gases that you look at in real time, because you don't have time to do anything more than that. Great technique, great technology to have in all your high vacuum applications. Okay. I was going to mention one. So the way it works is you have this little box. It's a quarter-Dean kind of box that connects through a cable to the probe, and this is the VQM itself mounted to the vacuum system. Other things that you can do is, here's the VQM mounted on the vacuum system right here. Here's the display, and here's the cable. Actually, this is the computer with a display, and here's the cable that connects to a VQM that is sitting over there. So one of the things that you can do is remote measurements with a VQM. For example, if the chambers are too hot, or you're in a radiation environment or things like that, you can always mount the VQM sensor in the radiation area and then bring the signal back to the unit, something that you cannot easily do with quadruples. Okay? So I'm going to skip a bunch of this stuff. I hope you can take a look at it on your own. Lots of fun advantages on this technology, but now I want to go to the final stage. My favorite subject, go back to this proactive monitoring, and talk a little about the following the water concept. And, depending on how we do, then we can go into a section of Q&A. Okay, so proactive monitoring. We go back to our scenario of, we have a vacuum chamber, we pump it down, all the valves are closed, we're just pumping it down. we expect to achieve a specific target base pressure in our targeted pump down time, and we're looking at our watches and we're not anywhere to hitting our base pressure in the amount of time that we expect, that we're used to from day to day. And there we are, we're sitting there contemplating, why isn't it pumping down? What is wrong, right? And again, we are asking ourselves all these questions. Is it a leak? And particularly if we weren't proactive and we didn't have an RGA and we didn't do any monitoring up front, right? We'll be asking ourselves, is this a leak, or were my samples too wet, or do I have contaminant? Did I forget the yellow handle screwdriver inside the vacuum system in the last modification that I did? The ion gauge alone, or the total pressure gauge alone, is not going to give you the answer. We are going to need partial pressure information to do this. And if we do things right, not only will we include partial pressure information in our measurements, but we will also do this proactively, okay? And this is what we're going to be talking about now. So I like to talk about reactive vacuum system monitoring and proactive vacuum system monitoring. Reactive monitoring is what unfortunately I see most people do. And so this is what happens. Most vacuum users start their pump down with the assumption that all is well. I didn't touch anything. I didn't touch the O-ring on my door. I put in good samples. I bought my aluminum foil from the same guy that I bought it last time. Everything should be great. For us, all our components were washed. Pete did his job putting it together. He was wearing gloves. Everything is good. So the assumption is everything is going to be okay. So I'm going to just pump down, and I'm pretty sure that in 2 hours I'm going to get there. So only a few users will proactively leak check their systems once the load lock is closed, which is a time-consuming process in itself. So the majority of people will close the door, start pumping down, and wait. And one of the reasons they do that is because the most common way to do proactive diagnostic on your system is to do a leak check, and leak checks take time. And nobody wants to spend the time doing that. It's time-consuming. They're usually, the leak detector is shared between different people in the facility. They gotta go find it, blah, 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 so they don't do it. Now, if the vacuum system fails to achieve its base pressure within the expected usual time, then we start the desperate troubleshooting procedure, right? The firefighting team is called, and we start what is going to be a reactive troubleshooting process. This reactive troubleshooting diagnostic procedure is, in my opinion, too costly, and it affects your throughput. So what I am here to tell you is that if this is your business and you're doing pump downs all the time, you got to start taking proactive measures instead. And the methodology that I use to do this all the time is what I call the follow the water methodology. So what does proactive monitoring entail? The question when we talk about proactive monitoring is, what I'm looking for is, can we identify pump down delays early on and troubleshoot the chamber or the vacuum system before wasting any process time? We have it here all the time, right? We load our 30 units or 50 units, 50 VUTs, right, or gauges into our chamber. We start the pump down, and we get to, and we start the pump down, right, and then the RGA is not working or whatever, at that day, or, they're replacing the filament or whatever it is somewhere else. And we don't do the proactive testing, and sure enough, the system takes 4 hours to pump down. If we had had the RGA there, we would have been able to identify problems early on, like I told you before. So what are all the things that we can do with the RGA or whatever technique we use to identify this problem before we waste all this time, right, and we lose a run for us, which is actually a lot of money for a company, right, of cages to be shipped. The other question that I have too, can we avoid having, when I talk about proactive monitoring, can we avoid having to do a time-consuming leak check every time the load lock is closed? I know a lot of you probably, because you're so tired of leaks, may be doing proactive leak checks every time. That might not be the best way to go about doing this. They're still time-consuming. They require people being involved. So that's all hands on deck while you're doing that. Is there a way to do this without having to go into this expensive and complicated helium leak detection procedure? So the question is, can we identify potential leaks in the system right away without using a helium leak detector? And bottom line is, can we easily identify a root cause for pump down delays? So what I suggest here is that you follow the water in your system. So the idea is, this is what we've been talking about before. We look at some spectra already, and like I said, I believe in the power of repetition. This is kind of how it all works for me every day when I'm trying to do diagnostics. Follow the water. Pump down starts. As soon as you reach a pressure at which the RGA or your VQM, which is the other technology that we talked about, is available, you start tracking water on your system. So what's going to happen, right? We talked about this before. As you start pumping down, the loose water starts coming out. Water is going to dominate the gas composition. So as the pump down starts down, you're going to be at about, as you turn your RGA, you're going to be at about 95% molar fraction of water in the system. At that point, right, you're just monitoring the water in the system. All you can do right now is, water is coming out of the walls. You got to wait a little bit until the water starts to go down, and you get closer to the walls, and the more tightly bound water is in the system. What I do at that point is I wait until, particularly in my turbo pump systems, what I will do is I will wait until the water gets to be about 75 to 85% of the concentration of gas in the system. And you can do that very quickly. You just look at your RGA spectrum, right? And you look at the water level, right, compared to the residual gas in the spectrum. And I'm going to show you how to do that in a minute. And at that point, right, at that point, what you do here, hold on. At that point, when you reach 75 to 85%, you start very, very carefully monitoring what the residual levels are. And what you're looking for is everybody else other than water, right? Is there any peak in that spectrum that is higher than your target base pressure? If the air peaks, right, the nitrogen and oxygen peaks are higher than your target base pressure, then you got to stop right there. If the contaminants like oil, any one of those peaks from oil or the sum of those peaks is greater than your target base pressure, you got to stop right there, and you got to do something about contamination. The bottom line is, as soon as the water, right, starts to go down, you achieve about 75 to 85%, you got to start looking everywhere else for the residual gases. And if any of those levels are higher than your target base pressure, you got to do something. Okay? So how do you do this? By following the water. Once the water pressure, the water concentration goes to the 75 to 85% level, and you start looking, what you will do, this is what I typically do, is I look at my mass spectrum and I integrate the partial pressures between 20 and 100 AMU. I just add them all up. I grab the spectrum, I'll add them all up, and I look at what number I come up with. And I consider that to be the residual partial pressure in the system. And then I compare to that residual partial pressure to my target base pressure. The requirement in my system as I pump down is that those residual partial pressures need to be lower than the target pressure I'm going to. So that is the requirement. If, for example, and I'm going to show you in the next slide how this works. So here's the spectrum, right, that I collect early on during the pump down. Here's my water peak, and there's the rest of the peaks. Water in this case is at about, 70%, something like that in this spectrum. And I'm looking at the residual gases between 20 and 100 AMU. If any of the peaks in this area, right, for example, say 28 and 32, go above my target base pressure, I don't need to wait any longer. I already know that I have a leak in the system, and I got to go start a leak checking procedure. I can typically do this in one of my vacuum systems within 5 minutes of a pump down. And I save myself the 2 hours that it's going to take for the water, right, and the rest of the contaminants to go down and reach the base pressure. If, for example, I start and any of the contamination peaks is higher than my target base pressure and the high molecular weight contaminants, those are not going to go down easy. I'm going to require a bake out. That is the time to stop and say, bake out the system now, try again after the bake out is completed. Or maybe you're going to turn on the internal lamps in your vacuum system. So I call this follow the water because the way I do this is I start by looking at the water levels at the beginning. I know my water is going to be 95%. As soon as I hit about 85 to 75%, I start looking at the residuals in the system compared to the water levels. And if any of those residuals goes above my target base pressure, right, or the sum of the residual goes above the target base pressure, I already know that I have a problem. There is no reason to wait, right? So what happens if the residual partial pressure is greater than the target base pressure? Well, the first thing that I do at that point, right, is I perform a leak check on the system to determine if residuals are due to air leaks. So, in other words, if I'm looking at the spectrum and I say, look, my 28 and 32 peaks are high, but I am not sure that I have the right 4-to-1 ratio, what I will do right away is I'll spray some helium or I'll spray some Freon around the system to see if I have a leak. If a helium leak is detected, right, then I go, the helium goes up, then I go and pinpoint the location, and which means I have to, and then at that point, once I know where it is, I stop the pump down and I fix the issue. It might be that I found it on an O-ring on the port, and then I'll go, take the O-ring out, I'll re-grease it, whatever it is that you have to do. Now, if no helium leak is detected, I'm still looking at the RGA spectrum, then I know that the problem is something else, is some sort of contamination. I can go look at the spectral libraries to try to identify what the species are, or I can just do a preemptive bake out on the system and try again, okay? So this brings me to the last subject, which is that of helium leak checking. So as you can tell by now, I'm not a super fan of relying on portable helium leak detectors for your system, and the reason is not that I have any bias against the technology. It's super sensitive, it's super useful, and so on. But what I've seen over the years in multiple facilities is that it's the workflow around portable helium leak detectors just doesn't work. What I mean by that is it's very unusual that you will have helium leak detectors dedicated to chambers. They're always shared. They're never close to where you need to be. They're never available when you need them. They're not always properly maintained. They're not always used by the other people, right, in the facility properly. So you don't know what you're going to get. You might actually cross-contaminate your chamber by exposing it to whatever mistake the last guy used it. So I'm not a super fan of using them. But regardless, many processes and many factories rely on helium leak detectors as the only way to identify leaks. So, if I ask them, I say, how do you know you have a leak? They say, well, we bring in a helium leak detector and we have some helium tanks and we start the process. I also know, like in our case, right, where some process engineers will actually do this on every every time that the load lock is resealed. You know, every time the door is closed before they start a pump down, they'll bring the helium leak detector. They'll go through this very time-consuming process of helium leak checking the system. But at least they know there's not a leak in the system, and they have a much better chance of reaching their base pressure. So this is kind of the proactive guys, right? Other engineers will leak check only after a pump down delay is manifested. They'll bring in the helium leak detector after they try to pump down for a while, nothing happened, right? They didn't get to their target base pressure, so now it is time to start a helium leak detection. So, bottom line is, even though I don't highly recommend it, helium leak detectors are used, my biggest concern today is when you're looking at helium leak detectors is that besides all the other things that I told you, a lot of time is wasted with helium leak detectors because for most vacuum systems, they're just too sensitive. And I'm going to go a little bit into that. And they lead to a lot of false positives. So let's talk about that. I don't know how many of you use leak detectors, how many of you are used to these units, but I'm going to assume that you are. And I'm going to present you a scenario of what a typical leak rate in a chamber is. Let's assume a system with a target base pressure of 10 to the minus 7 torr. Okay, that's my, let's make it up. This is where you got to go today. And the system has a pumping speed of 100 liters per second. Okay, so where would you be able to say that there is, when would you be able to say there is a problem in your system? Well, you would be able to do this as soon as you know, if you're not reaching the 1 minus 7 torr. For most gauges, this is typically when the gauge fails to reach 1 minus 7 by 1 decimal point. So that means that you're sensitive to about 1 minus 8 torr of leak, right? A 1 minus 8 torr leak with a 100 liter per second pump corresponds to a 10 to the minus 6 torr liter per second leak of air into the system. So, and if you do this, for example, for low, medium, and even high vacuum, what you're going to find out is the majority of the vacuum systems, the leaks that actually matter to you are rarely lower than 10 to the minus 6 torr liter second. What this means, though, is that now when you look at the majority of the helium leak detectors that are used today on lines, most of them have anywhere from 10 to the minus 8 to 10 to the minus 9 torr liter per second sensitivities or detection limits. What it means is that for the same system we were talking before, 100 liters per second, they will be sensitive to a leak that only changes the pressure by 10 to the minus 12 torr. So what I do see a lot of is people spending time hunting for leaks that have absolutely zero relevance to their vacuum systems. So one of the things that you're going to have to do is if you do have a vacuum system that relies on a helium leak detector to do leak detection and a portable helium leak detection, understand what is a true important leak and don't spend time chasing leaks that don't matter. And I am telling you, I see that all the time. I see that in semiconductor facilities. I see that in universities. People calling me, we go through the numbers and they describe, the leaks. They think that maybe there's something wrong with the gauge that we should ship to them. And when we crunch through the numbers, we come to the conclusion that, the numbers they're looking at, they cannot possibly be relevant to their process. They're certainly not affecting their pump down times. So be very, very, very careful when you use helium leak detectors not to get yourself stuck with these false positives that have absolutely relevance in terms of troubleshooting your problems. Okay? So, bottom line, final thoughts. We are pretty much at the end here. If we kind of summarize some of the key concepts that we went through today, and I sure hope this was helpful to you, this is kind of a summary of the way I go about my business every day doing vacuum. Here's the list, right? The first thing that you gotta do as you do your process is you gotta assign a base pressure to your process. You gotta understand what is the highest pressure at which you can possibly start your process, whether it's a manufacturing process or an experiment. You know, you could say, ideally, I want that to be as small as possible. You can't do that because you're paying for it, you know, with pumps, with material selection for your vacuum system and so on. So you gotta be smart. You gotta go figure out. You gotta do the math. You gotta figure out what is the pressure that I need to achieve, the maximum pressure that I can live with, where I can run my process and I know that my yields are not going to be affected. So once that is done, then once you select your base pressure, then you either design or modify your vacuum system to provide an ultimate pressure that is at least 10 times lower than that base pressure. By doing that, what you're allowing yourself is some buffer by allowing this extra water outgassing window, right? So that you get shorter and more repeatable day-to-day pump downs. Once you know what this ultimate pressure is going to be, now you can use modern design, rigorous design methodologies to design your vacuum system. And I cannot emphasize enough, understand your chamber, know your surface areas, know your pumping speeds, right? Know if there are any spots where the conductance of the gases is getting stuck. Understand your chamber very well. The next step is use accurate gauging, right? Which is well matched to your application. You know, not only accuracy and repeatability, but also compatibility with the chemicals that you have. And then, of course, be proactive. Follow the water during the pump downs. Start looking as you start pumping down. Don't cross your fingers and hope that everything is going to be okay. Follow the water. As soon as you can turn on your RGA, and you know, this is the next bullet, right? Use your RGAs and your VQMs to monitor your system and process. This is totally priceless. Follow the water. As soon as you see the water drop below, you know, 75, 85%, start looking at the residuals. And if the residuals are higher than your target base pressure, then you're not going to get there. It's time to stop. It's time to do a diagnostic, look for leaks, fix the contamination, whatever, right? Whatever you need to do at that point. Don't waste time on wishful thinking. And the last one, which is not listed here, what we just went through, if you're going to rely on helium leak detectors, don't get stuck looking for the wrong stuff. Understand what is a significant or detectable leak in your vacuum system, and then only look for leaks that matter. Don't get stuck looking for 10 to the minus 9 torr-liter second leaks that don't mean anything to you. They'll take forever to find, and you'll fix them and you'll still be exactly where you were before when you do your next pump down. So with that, I have 5 minutes left, 5 less than I proposed originally. So I can take, if there are any questions, I'm going to take a look here. I'm going to see if I can answer some, and then we're getting to the end. You get to get rid of me finally. Okay. So here I have a question. For your semiconductor gauge accuracy check example, how do you set Q to be the same as S if you also have the uncontrollable leaks in the system? Well, you know, if we're talking about, if you're talking about same as S, if you have uncontrollable leaks. If you're talking about the calibration methodology that I was talking about before, where you introduce a known amount of Q into your system and then you look at the pressure. So here's the deal. Let's just say that your system has a leak right now, right? So your pressure is a little higher than usual. What you're concerned about is, well, I'm going to introduce some gas, but there is some gas coming in from a leak as well. So how do I know which one is which? Well, here's the good news. You can measure the pressure at the beginning before you introduce any gas, right? And then you open up the valve, you introduce new gas in, you measure the other pressure, and you calculate the difference. That difference is what you use now instead of what would have been before all of it, right? And that step in pressure that you have should be the same as you did the last time that you checked. or your gauge is losing sensitivity. I hope that makes sense. So in other words, and you know, of course, the best thing is to not calibrate your gauges when you have leaks in your system, right? You would do it at a time when you know your system is performing well, but the reality is, regardless, right, you will always have an initial Q in your chamber, right? Because there's always some gas present in the chamber. And what you're really measuring when you add gas with your mass flow controller is the delta in pressure that you're going to have. And what you want is day to day, adding the same amount of gas into the system, you want to have the same delta in pressure reported by the gauge. If you don't, or if that's starting to decrease over time, your gauge is drifting. Yeah, good question. I don't know, it's Ivan Spector, if you say it that way, but you know, it's funny you say this. Is there an advantage of the RGA? It looks like the VQM wins in all categories. There is one category where the RGA wins, and that is dynamic range. So the VQM is faster. The VQM, via averaging, you can get pretty good sensitivity. Here's the bottom line. Here's how it works. If you're consistently measuring pressures below 10 to the -7 torr, the VQM is the way to go. If you are working over a much wider range of pressures, all the way, you know, into the high -5s, you want an RGA. But if you're consistently below 10 to the -7, it wins every time. Doesn't matter what you do, it wins. And I encourage you to look into it. Otherwise, if you have a much wider range of pressures, as you go above 10 to the -7 torr, particularly because of dynamic range advantages, so being able to see little guys next to big guys, right? The RGA might be a better way to go. And certainly I can. If you want to send me an email and discuss this because it's something that maybe matters to you, we can talk about it in more detail. Or it's something that I go into in the RGA course. Let's see, here's another one. I am using an ion pump and its current pressure reading is not accurate. Can I still assume its pumping speed is correct as long as it's maintaining vacuum? Its current pressure reading. Yeah. Yeah, I mean, lots of people, particularly in extreme high vacuum conditions, a lot of people use ion pumps to measure their pressure. It's okay, it works, there's a lot of sensitivity there. It's not very reproducible, it will drift over time, but it's a good way to do it, particularly if you are at ultra high vacuum conditions. Then what coatings are best to minimize outgassing? Oh boy. That's a whole class all by itself. Let's see, in the few seconds that we have left. I have seen all kinds of things. It kind of depends too on what it is that is outgassing in your system. I really like, there's a lot of efforts right now on ALD coatings of chambers. I've seen a lot of aluminum oxide work being done. I've seen Silco steel being done. I've even seen ITRA coatings being done. Aluminum chambers are great, but again, lots of tables out there that you can go and consult, you know, online as well, or send me an email and I'll be able to help you some more. So anyways, I think we are at the end. I hope you all got something out of this class. Like I said, it's the first time around it. I welcome your comments. Please fill out the survey. We can only get better from here, so we are in continuous improvement, and have a good day. Thank you all.